Welcome everyone. A very good afternoon to all of you and welcome to Aachen for everyone who's attending the event in presence here. And we also have a lot of participants attending online. Can one of you just give me a shout out in chat if you can hear me loud and clear? Very nice, thank you. So, we have a workshop here on technologies for biofuel hybrid microgas turbines. And I'm stepping in. My name is Sangeeta Ramaswamy. I work at OV, responsible for the EU projects there. And I'm stepping in for Simon Minute. Unfortunately, he couldn't make it today, so you have to bear with me instead. We have a packed agenda today with a lot of presentations from various perspectives of how to shape the future of sustainable energy for the industry. And it all centers around the project Fit for Micro, and you'll hear a lot of presentations about the projects and also with the different technologies which are which the project deals with. But before we begin with that, we wanted to also give you a small welcome from my institute, OV. And for that, we have our CEO, Dr. Wilfried Plum, who will give you a very small insight into where you are today and who are your hosts.
Thank you very much for being here, for the invitation. Dear ladies and gentlemen, I am delighted to welcome you here, physical, over the roofs of Aachen, and on air, maybe all over the world, for this workshop Sangeeta told us. My name is Wilfried Plum, and I'm the Managing Director of OV Science for Fuels, since 5 years. So shortly after the lunch, a lengthy description of our institute could be the best way to take a nap. So sit back, relax, and close the curtain. So don't worry. I don't want to bore you with too much description about our projects, about our organizational structure or our funding bodies. I want to tell you what OV and his employees are standing for. We are a non-profit organization, and we are financed by 80% by public-funded research projects, national projects or EU projects, just like Fit for Micro, as we have been here. The rest, the remaining 20%, we have to cover by so-called special purpose operation. It's when we make specially research projects for the industry. So in this picture, you see the current staff of our institute. They are all working here, and some of you met them when they are looking in our laboratories. So over the past 25 years, more than 450 people have been worked at OV. As young scientists, for example, process engineers, mechanical and automotive engineers, chemists, physics, electrical engineers, and also exotic, such as a textile engineer. And they all do good work for us. But also we have technicians, chemical laboratory assistants, and people in the administration. Around 40 employees have completed their doctorates with us, and we are in contact with them to give a good network in every research area. We have published our knowledge in more than 500 lectures and presentations, and over the years our institute has always been multinational. So with people from 7 different nations, we work together today. Our work is characterized by the interaction of different skills, knowledge and backgrounds. The project managers discussed with our technicians how the test benches should be built. You have seen our test benches in our laboratories today. They are special, they are unique, and if there are problems, we have a small but an excellent team of technicians who've been able to react quickly and individual and make the test bench run again. And this is one of the foundation of our successful work. Let me briefly show you on a timeline about 25 years of research for energy transition. OVI was founded in 1989 as Öl-Wärme-Institut, OWI, translated to Oil and Heating Institute. The trigger was the introduction of low sulfur fuels in the German market. This gave rise to a number of questions for the customers, for the contributors of the new fuels. Do the heating systems work with the new fuel? How do the materials get on with the new fuels? In other words, how do new energy carrier work in existence infrastructures? What aspects need to be considered to ensure that the technology continues to function without problems? These questions are still at the center of our research activities today. The energy carriers are no longer just liquid. Hydrogen, ammonia, methanol, or every electric. But the questions are the same. And it's not limited from the beginning in the heat market. It also goes to mobility and also to the energy generation in the high temperature range. The next step after we make research on low sulfur fuels, it becomes the introduction of the first generation of bionic fuels. Even, for example, what we call in German famous fatty acid methyl ester. So we used it in Germany to 100% driving in cars. There are some problems, and we look what happened if we make mixture with heating oils, and does the infrastructure still works. In 27 we became what we say in German an Institut der RWTH Aachen. It means OVI is affiliated to the RWTH. And this is important for us in two respects. On the one hand, it showed that our work satisfies the scientific principles of RWTH Aachen University, and on the other hand, ensured our proximity to the one of the most renowned university of Germany. And after the first generation of bionic fuels, there comes the second generation of bionic fuels.
We have to up a little earlier because we have to go to the next presentation.
Okay.
We're running out of time.
Okay, so I have 1 minute. Okay, so we are still working not only on fuels. You see it on the things we've done. We are doing a lot of things in, let me say, in three pillars. That is, is first energy carriers, high temperature technologies, and energy systems. Our research findings can make small contribution to the solving the problems of the climate change. This is what drives my colleagues and me. Thank you for your attention. I had a lot of things I would tell you about OVI, but the time's run, and so I wish us a very success of the rest of this event. Thank you very much.
Thank you, Wilfried. Thank you, Wilfried, for the detailed explanation about OV and its activities. And I think you can also link the homepage on the chat so that anyone who's interested can have a look. Now we move on to the main topic of the day with an introduction to Fit for Micro project. Before we move into it, I just want to quickly remind everyone who's participating online that we would really encourage you to be a part of the event by asking your questions and leaving your comments on the chat. And we'll have a question and answer session at the end of every presentation, if the presenters are on time, to have this interaction. So moving on to our first presentation, it's by Michelle Delaney on the Fit for Micro project and introduction to the project. I don't think you need the mic, you can just...
Yeah, okay. So can you hear me well? Well, you, I know, but yeah, it's okay? Okay, good. So thank you, Sangeeta. And first of all, thank you to Siri to have organized all these nice workshops. So we are in a very nice place, so thank you. And it's my pleasure actually to introduce you the Fit for Micro project on behalf of the consortium. So I'm the CEO and founder of MITIS, which is the coordinator of this project, and we are located in Belgium, and we are developing microgas turbines and other type of power conversion devices such as fuel cells and also high temperature SOFC recently. Okay, not moving.
You have to press on the center, I hope.
Center?
Yeah.
Okay, oops. Sorry. Wow, can I come back?
Yeah.
Okay. Okay, good. Yes, so what is up? I mean, we have a problem because it's not I'm missing some slides. Can you check? Where are all my slides?
Hidden.
It's hidden?
I guess.
Can you open it? No? Because it's an important slide. I'm missing the first slide. Can you just unhide the first slide, which is hidden? That's quite important. Thanks. I haven't checked for the hidden slides. Okay, good. I like that picture, although it's a little bit harsh, but we know what's happening today. We have our climate change, and now we are feeling actually the impact of that climate change quite importantly in every country. Look at what happened actually in Poland, Czechia, and so on. It was 2 years ago in Belgium. We had 40 people dying in flooding, which had not happened actually. Okay. Which had not happened actually in the last 70 years. So basically, our project, and my talk will be essentially to introduce you the objective of our project, highlight what we are doing. I'm not going to be talking too much about results and so on because we don't have time. So if my talk is successful, at least you will know what we are doing into these projects and what is our objective. First of all, actually, the context where we are working is basically related to the European building sector, and especially the way we are heating that sector and also providing power to the sector. What you may know, and numbers might change from years to years, so my numbers might not be exactly, but they're probably good into the ballpark, as we discussed in the lunch. So European building sector is consuming 40% of final energy, totally consumed in Europe, which is huge. Still emitting about 36% of the total greenhouse gases. So this is a heavy contributor to the climate change. 79% of all this is actually for heating, cooling, and domestic hot water production. And for producing all of this energy, final energy, actually we are still depending basically on 75% fossil fuel, which mainly is natural gas, some heating oil. I guess it's about what we are actually using. And at the same time, we know that we need to go to net zero by 2050, which probably, you know, it's more like a dream than anything else, but actually we have to give it a try. And there will not be actually more than 12% of all the buildings which will be deeply renovated, which means that probably 70% of all the current buildings will still be there in 2050. And we still need to heat them, and we want to heat them actually with something else than fossil fuel. So, first of all, there is an urgent need to switch off fossil fuels, but how to do it? So, that's basically what we are trying to address in our project. Okay? So, what are the ways to switch off this fossil fuel use? But first of all, there will not be a single solution. Certainly not. And our solution that we are developing in Fit for Micro, let's say, is one of many. Okay? And I would say three things which probably contributes well to these solutions is the fact that everyone needs to reduce the energy consumptions. Means we need to reduce the heat demand. We need to be more efficient. We probably need to have better distribution networks. Instead of using fossil fuels, we might want to need, and we probably need to use biofuels, new kind of biofuels, mix of green electricity, low carbon gases, and biomass, biofuels out of biomass, biogas. And probably also, we need to introduce, as much as possible, heat pumps, okay, whenever it's possible to use them. Although this poses also a great potential burden on a grid network, and you might know that in some areas in Europe, for example, the Netherlands, grid networks are already totally congested. So this is a problem. So what we are trying to do in Fit for Micro is actually to combine some of these elements together. So is there a pointer? No? No pointer. So we are actually looking at producing biofuels of second or third generation, I would say, which are using residues or organic waste. So there's no question here to use, I would say, crops that we are growing into a field in order to transform it into a biofuel. No, those will be organic waste and residues. The type of biomass or biofuel that we'll be producing is a liquid fuel, and we call it hydrotreated pyrolysis oil. So this is a liquid, and being a liquid, it means that it's kind of nice actually to transport and to move. And this is a possibility to replace, for example, heating oil, which is still heavily used. In Belgium, for example, there's still a lot of households, especially in villages, for example, in the countryside, which are using heating oil, because there's no way actually to have something else. No grid with natural gas. You can use propane, but it depends if you like to have a big tank in your garden. Some people don't like. So heating oil is actually still used a lot. It's being phased out, and biofuel, liquid biofuels can be actually a good replacement to this. Then the idea is, what are we going to do with this liquid biofuel? Basically, we would like to produce, of course, heating, but we want also to produce power, because probably the best thing to do with the fuel is actually to convert it to some sort of electricity. So we want to convert it to electricity, and for this we will use a microgas turbine of new generation, which is what we call micro CCHP for heating and cooling. So we'll produce heating, we'll produce power, we'll also produce cooling in a decentralized way by connecting to the microgas turbine additional elements, which are either vapor compression heat pump or adsorption chillers if you want to do cooling. So this solution is basically to go from organic waste, meaning renewable, to very efficient power generation, totally decentralized system. So we don't want to lose any bits and pieces of the good energy which is inside of our fuel. So that's the idea of the project. Then comes the big part. So we are basically halfway into our project. So this is 2 years. We are holding a workshop. We are holding a 2 years meeting in parallel to this workshop. And this is very interesting to listen to what the different parties and beneficiaries have done in the project, because now we are seeing puzzles, pieces of puzzles, which are basically created separately. Now they will come together. And so hopefully at the end of the whole project, we will have a nice systems demonstrated like I showed before. So this project is funded by the European Commission. It's a 5 million euro project running for 14 months, started October 2022, and you see the list of partners here. We have Métis, the coordinator, working on the microgas turbine together with the University of Mons. BTG is developing the biofuel together with OE. OE is actually working with us on improving our combustion for liquid fuels. Fahrenheit and Fraunhofer are working an integrator of the whole system, Fahrenheit bringing the adsorption chiller, and Fraunhofer being responsible of the overall integration of the system. And we are supported by University of Aalborg for life cycle analysis and ETA for disseminations. And we have also Cogen Europe, the association of all cogeneration institution companies in Europe, which is actually bringing us a lot of insight of how things are moving in terms of the policies in Europe. We have multiple work packages. We have 7 in total. 4 are basically technical, and they are parallel to just what I showed in terms of the solution, meaning we need to work package 2 on biofuel, work package 3 on combustion, work package 4 on the conversion system, which is this microgas turbine, and work package 5 on the integration of the system. Life cycle analysis in WP6, and policy and market exploitation in work package 7. We are quite lucky that this is a research innovation action, meaning it's quite well funded by the European Commission. So impact at the end of our projects should be that we obviously bring to the market, or potentially to TRL 6 or 5, something that can replace oil-fired boilers with a much modern, high-efficiency, biofuel-based micro-combined heat and power and cooling. We are small companies in the project, Métis, BTG, Fahrenheit. So our idea is also that European Union is obviously helping us in being more competitive with respect to the European landscape. We have an important aspect which is related to the cost of biofuel. You can imagine, I mean, it's easier to drill to get oil and to create, let's say, heating oil, actually, from something that you find in a reservoir in the ground, than making a biofuel. So we need to be able to decrease the price of this biofuel, and one way is actually to use residuals and waste. And obviously, we also want to be good in terms of environment sustainability. That's why we are focusing on very low emissions, flameless combustion, as well as using residues, forest residues typically, and green hydrogen to produce our fuel. So I will jump very quickly into the different work packages. So how many? Oh, still 5. Okay, so it will be very quick. One aspect which is very important is the production of the biofuel. So typically we want them to be economically viable, and also we want them to be sufficiently powerful. And so there's many ways to make these biofuels. And so what we are testing is different composition of those biofuels, where we are actually waiting in between the cost of this biofuel and the energy content of the biofuel. So what we want, obviously, is to make it as simple as possible, but still being able to combust it in a low emission way so that it's cost effective. So this is where we are trying to be on a scale of hydrogen to carbon content with respect to hydrogen, knowing that because we need to put hydrogen in the biofuel, it's costly, mainly. So that's the process actually of producing this biofuel, which is called hydrotreated pyrolysis oil. And so we start from residues, like forest residues. We do fast pyrolysis. So this is made by BTG. They have their reactors, and they produce what we call HPO, which is the hydrotreated pyrolysis oil, after which we have put hydrogen, well, before which we have put hydrogen into it. From there you can go to the distillation and produce the classical fuels, but we don't want to get that far because that means we're increasing cost to our fuel. We would like to look at what is basically the grade we can have and still have a good combustion. There's a lot of activities in the projects which are related to removing the organic residues. So look at how to remove nitrogen because that can produce NOx actually when we burn it and so on. Distillate and so on, standardization. So that's activities which are part of this HPO production. Now we want to, we have a nice biofuel which is not too costly, which has the right content in terms of energy. We want to produce heat in order to run the machine. And we are doing this by a novel technology for combustion that we have developed together with the University of Brussels. And you will have a nice presentation by my fellow, actually, which is holding the patent with me on this. So we developed this together with Alessandro Parente. I want to name him. So we are actually improving this flameless combustor in order to actually being able to burn liquid fuel in a very efficient way, low NOx, low CO. So I'm not going to talk about flameless combustion. He will talk about it. So OE has installed actually a test bench in their facility where they are testing our combustor, which is there, and trying to see if by burning the different grade of HPO, whether we can still reach low NOx and CO. I'm not showing the last results, but the last results are really good, actually. So we are in the single digit for NOx and for CO, which is very, very good. So we've been working, for example, on atomization, and those have been subcontracted to the University of Brussels by OE to improve injectors, actually, to get very nice atomizations, to be able to burn. And also, one of the problems, actually, when you're in a microgas turbine, it's pretty hot. You have also nasty, actually, exhaust gases. You want to see what kind of material you're using. So we have a full campaign, actually, on what kind of material can be used inside of a machine, especially into the recuperator, which is a very complicated heat exchangers. So we are testing different materials here. And we are happy to see that the one that we have chosen as a material is a good one, but we know also it's a costly one, which is the more annoying part. Going to WP4, which is the engine. The engine is a new cycle. So we have a microgas turbine with two stages, a low pressure stage and a high pressure stage. The compression is done in two stages with an intercooling. So we are reducing the work of the compression. And we are putting two combustors because then we are as close as possible to an isothermal expansion, which means that we have also a better efficiency into this expansion. So we are bringing two flameless combustors inside of this. And our objective is to reach 35 to hopefully 40, impossible 40, we know it, but we would like to lean towards 40% efficiency because we need a very efficient electric production machine. In addition, actually, we are introducing into our microgas turbine a recuperation of the heat through the injection of steam. So we produce steam at the exhaust, we introduce it back, and we can gain electrical efficiency, and also we can balance the amount of heat with respect to the amount of power which is produced by this machine. This machine is based on airfoil bearings. You will have a presentation on it later. So no oil into it, flameless combustion, super low NOx. And also we are producing a DC current, which then is injected into the grid to an inverter. So the machine does not suffer from the usual problem of piston engines, which is high maintenance, high emissions, synchronization to the grid. That's how it looks like. So I'm not going to go into it. That's our machine. So we have patents actually on the compact version of these turbo generators, and you have a quick idea on what is here, the bearings, which actually created a lot of difficulties to design, but now it's working very well. Yes, 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 I'm going fast. So work package 5, fuel systems, work package is on the integrated systems, and there Fraunhofer will actually combine everything together, and we started by creating It's quite sophisticated Excel sheet which is able to model in a full year actually how the system will behave and produce electricity and heat depending on the evolution of the climate. So this is a very interesting techno-economical analysis we can use to qualify what kind of buildings we can use. And also we are integrating two types of heat pumps. That's a vapor compression heat pump based on propane that we have developed in another project which is tested by Fraunhofer. And there we have a silica gel adsorption chiller developed by Fahrenheit will be integrated into the system at the end. So unfortunately I have to skip what it's very difficult for me to talk about. So it's easy then, which is work package 6 on life cycle analysis. So I'm sorry, my friend Søren, but it's very difficult. And yes, so we have a full life cycle analysis actually of our system and gender equality evaluation. And also Cogen Europe is actually bringing us a lot of insight of the evolution of the policies in Europe, which are difficult to follow and which are interesting to know how to position our system. And if you want to know more, I mean, we have, of course, we are present on the social networks. So we are on Twitter, we are on YouTube, we are also on LinkedIn, and you can visit our websites, you can send us email, and we are very active on this. So thank you very much. Question?
Maybe we can have one question. Or we'll go into the details now in the next presentations. We'll go into the details. There is a question online. When is the project expected to complete is a question online.
2 years.
In 2 years. 2026?
Yes, 2 years from now.
Yes. All right. I think there'll be more questions when we go on to the details in the next presentations. This event was also an excellent opportunity to have a discussion with other topics, with other technologies and initiatives around Europe, which are working on the same topics of industry decarbonization. And in that respect, we have our next presentation from a guest speaker. The topic is hydrogen and ammonia for industry decarbonization, the role of diluted combustion technologies. And our speaker is Alessandro Parente. The floor is yours.
Thank you very much.
Don't worry, I'll remind you.
Yeah, it's okay. Good morning, good afternoon, everyone. So actually, for me, it's still morning because I got stuck 3 hours in the train from Brussels to here. But anyway, I'm very glad to be here, and thank you very much for the invitation. I will talk about our recent work about hydrogen and ammonia in the context of novel combustion technologies. I will try to frame this in the context of hard-to-abate industries, and I think it makes a very good connection with what Michel was talking about. So let me introduce this by a little bit how Michel was doing it. So we know that we have already almost depleted our carbon budget to limit the temperature increase to 1.5 degrees. And as Michel was showing in his images, we are already suffering many consequences, and so we have to act very fast. Just for you, maybe to take note of this, there is a very nice but also very concerning work from the Swedish photographer Christian Aslund about the comparison of glaciers at 100 years after, so in the same location. And so you see, this is one comparison that shows at the same time of the year the difference that you would see if you observe the same glacier. So there is a full there's a full collection of these kind of pictures. You can find them by looking at this name. Okay, so we talk about electricity and decarbonization, but when you actually talk about decarbonization and you look at electricity, this is just what we call the tip of the iceberg. What is really complicated and challenging is to actually decarbonize heat. And this is actually the headache, I would say, of the energy transition. It's about 40% of, it's responsible for about 40% of global CO2 emissions. Now, if you look at the sectors that need to be decarbonized, and if I quote here somehow George Orwell, they are not all equal, the sectors. Some of them are more equal than others, because if you look at high temperature heat, non-energy sources like production of ammonia and methanol, or if you look into high density local energy sources for shipping, trucking, and aviation, you realize that very soon that the direct electrification of these sectors is challenging, if not impossible, and that other strategies have to be used. There is actually a report from the International Energy Agency that actually points that very clearly. There is a big elephant in the room here, and this elephant in the room is the high temperature heat, high grade process heat, which is very challenging to electrify. Even today, with the technologies that we have, it is not clear how we can electrify these processes. Now, these hard-to-abate industries, so the ones that I showed before, are a real headache in decarbonization because, of course, they contribute to 30% of world greenhouse gas emissions. They also contribute to a large share of CO2 emissions. But besides or beyond everything, what is really challenging here is that these are very integrated sectors. They contribute very strongly to the economies of our countries, and they are also needed in a net zero world. So this is a real headache for decarbonization strategies. Now, if you look into the strategies that are put forward for these hard-to-abate industries, OHT-AIs, there are several, let's say, enablers that could be used. Of course, there is efficiency improvement. This is the first thing that we should look after. There is optimization, digitalization, artificial intelligence. I will touch a little bit on this. Of course, we should electrify as much as possible, where it's possible, where it's feasible. We should use, and this is something that Michel was mentioning, carbon neutral fuels. So, for instance, green hydrogen, but also we talk about other kind of fuels. When it's sustainable and economically viable, we should do carbon capture using biofuels, improve circularity. So there is no one measure that it's alone sufficient to get to this goal. We should actually use the combination or a combination of all of them. By the way, if you're interested, this is actually coming from this high-level master plan that was issued by the European Commission. Now, synthetic fuels, and Michel touched on this, are key enablers, of course, are one of the possible enablers of these solutions. The idea that is actually developing is quite simple. We cannot rely on renewable energies for direct electrification, but we could, at times where we have excess of energy, use this energy to produce renewable synthetic fuels. This is what I mean with RSF, so renewable synthetic fuels. And then this could be used on demand, of course, to produce it and electricity. But of course, a key point here is that whenever or whatever fuel I produce at this stage, I need the appropriate technologies to actually convert them, because otherwise, I mean, I can produce whatever fuel I wish. If I convert them non-efficiently and producing pollutants, then I would be, I would still have a big problem. So among the renewable synthetic fuels, of course, we can find hydrogen, ammonia. These are interesting because they do not have any carbon, so they will not produce any emissions of CO2. I could go also and produce e-methane or methanol by synthesis. This is possible. I need a CO2 source which is CO2 neutral, otherwise it doesn't make sense. What is interesting of these fuels is that, of course, I can rely on technologies that have been already proved efficient or flexible for this kind of fuels. So these are fuels that we know a little bit better. But then the technologies, as I was mentioning, they should be technologies that can couple can solve. So this triangle here is taken from this energy trilemma, where you actually have to couple pollution, environment, cost, and security drivers. Now, if you decline this into combustion, of course, what we have to be careful of is technologies that do not emit or significant pollutants, that are cost-effective and efficient, that are also flexible with respect to the choice of the fuel. Okay, so what technologies can we use? Now, combustion scientists have faced for many years the so-called combustion dilemma, meaning that whenever you actually increase the efficiency of the process, you also usually have an increase of the pollutants. And the example, typical example is NOx emissions. So if you increase the temperature, you know that your NOx emissions will increase exponentially with the temperature. And so there is usually a trade-off that you would find between these two objectives if you use a conventional combustion technology. Now, if you rely on something like flameless or mild combustion, then you can actually have invisible and ultra-low emission flames. And this is actually change a little bit of paradigm as you see the combustion process. Your combustion systems as a whole becomes like a reactor. And in a reactor, likewise in a reactor, you can actually tailor the condition of your system by choosing properly the operating condition of the system. Now there are requirements to actually work in flameless or in mild conditions. And these requirements actually imply that you need reactants to be above the self-ignition temperature of the fuel. It doesn't mean that your reactants must be preheated outside, but also by internal recirculation, they should be above the self-ignition temperature. Also, the system must be very diluted, and this means that locally, this is a local requirement, the delta T is actually smaller, so the increase of temperature due to combustion will be smaller than the self-ignition temperature of the fuel. Okay, so this actually can be accomplished in several ways. The easiest is to actually use internal gas recirculation. Also, you can combine this with the external gas recirculation. Okay, so now this technology has been already proven. It's used currently today, for instance, in material treatment. I think in steel annealing, glassmaking, maybe not so much, but still treatment. This is actually the state of the art. It's also very interesting for its fuel flexibility. In fact, it is a technology that is very, very interesting for low calorific value fuels, high calorific wastes, H2 enriched fuels, oxy-fuel technologies, all of them. And also in the field of gas turbine, it holds very much promise because of this other feature that flameless combustion has, to be very noiseless and stable, which is an interesting feature, for instance, for gas turbines, both gas turbines and micro gas turbines. Okay, now let me dive from now on a little bit into these new fuels, what kind of questions they raise when it comes to combustion technologies, and also how can we use existing systems or develop new systems to efficiently convert these kind of fuels. Now, imagine that you have to convert or retrofit an existing system with these new molecules. It could be ammonia, hydrogen. Then the question that, of course, you might have could be, okay, what would be the impact of the different combustion processes on my process? Will I have any impact of this combustion atmosphere, for instance, on the system itself? Michelle was mentioning materials. Materials with hydrogen and ammonia could become an interesting point of attention. What would be the impact on the pollutant emissions, for instance? If I'm treating any product in the furnace or in the system, will I have any impact on the product quality? So these are all questions that you want to address. And of course, when you look at these fuels, I mean, they have very different properties. And so here I'm trying to actually compare them to something that we know very, very well. So if you look at ammonia and hydrogen, I put them on two opposite sides. Why? Because one of them is very, I mean, eager to react. The other one doesn't want to react at all. And in the middle, I've put methane as reference. It's something that we know very well. So if you compare them with, in terms of combustion properties, for instance, adiabatic flame temperature, you see that ammonia is the lowest one. Methane is in the middle. Hydrogen is about 200 degrees higher than methane. If I continue, I look now at the flame speed. You see that hydrogen has a very huge flame speed, and it's it's almost impossible to burn ammonia. It's a very, very small laminar flame speed. This also means, for instance, in gas turbines with premixed flames, that you might have very strong problems with flashbacks, so safety problems, safety issues. The other thing that is important also is to look at the heating value. And so if I look at the heating value here, I notice that in terms of mass, hydrogen is the highest one. But this is not really relevant, because what really matters is the volumetric. So because I need to store this somehow, right? And so if I look at this, I actually see that ammonia has some advantages over hydrogen, because hydrogen I have to store it at 700 bar, and the volumetric, let's say, energy density is very low. Ammonia is closer, let's say, still lower than hydrogen. And it's actually easier to transport and store, and it's liquid at 9 bar. So this actually explains why we are even looking into ammonia, because otherwise burning ammonia would be a very bad idea, right? So you wouldn't never burn ammonia. It's just, let's say, a carrier of hydrogen, and this is something that people are looking into. I want to make a point here. I think it's very important. When we look at these systems and these new fuels in these systems, how they behave, we have to really be careful about the scale at which we do these tests. In general, we have a lot of tests that are performed lab scale. These are very important. I mean, important. They are actually shedding light on fundamental properties. But here we have, of course, a lot of high fidelity data, but we are very, very far from the application. In theory, we would like to have the real thing, right? So we would like to have data at the application scale. But in general, the issue here is that we have very limited data, and this is both in quantity and in quality. So what is really emerging now is to have these intermediate scales, so scale bridging kind of systems where we actually have a physics that is very similar to the application, data that is not as detailed as at the lab scale, but still quite accurate and rich. If we look at mild combustion, there are a number of systems at lab scale. So for instance, many numerical models have been developed through the years on these simple reactor burners or let's say canonical flames, in particular this jet-inert co-flow, so where you replicate the flameless behavior by having a co-flow of combustion products. And more recently, there have been a surge of more complicated systems, like lab-scale furnaces. So this is the one that was one that is installed in Delft, one that was in Mons. There is also one that was studied for a long time in Hagen, in the group of Eindpitch. And so these, I mean, have kind of behavior that is actually closer to what you would find in a real industrial system. Now, ULB, we have two furnaces. We have two systems that we study. We use for studying these new fuels. One is a furnace. It is a semi-industrial furnace. It actually mounts an industrial-grade burner, and it was built by the German company WS, you might know, Wärmeprozesstechnik, the inventors of flux, flameless. And the other one is the combustion chamber developed by Metis that Michel was discussing before. That is a stagnation point reverse flow burner for application in microgas turbines, and not only, of course. now this is a picture of what we would see in our furnace. This is not just switched off. It's still working. You see it from the glow that you get it inside the furnace, but we don't have any flame. We have single digits emissions. This is with methane. And so this is a flame operation. This is flameless. You see that, in fact, the fact you don't have a flame changes the radiation of the injector here. Okay, when it comes to these new fuels, the first thing I want to do is to actually have a look at what it means to have a flameless system. I actually told you that that the furnace is a flameless furnace. It uses a flameless burner, and that flameless combustion is very flexible with respect to the fuel. But then you might think now that whatever fuel I put inside the furnace, it will be flameless. So so for instance, let's put it like this. What do you think will happen if I take the same furnace and I inject hydrogen in the furnace? Would you see, let's say, a flameless behavior or not? Like a guess? No? Maybe the way I put it was a bit, but anyway. The point I want to make here is that when we talk about flameless, we should also always think about the combination of the fuel plus the burner plus the combustion chamber. Why? Because the fuel, of course, and this is something we saw with ammonia, hydrogen properties, will determine the propensity to burning. The burner will actually determine the mixing pattern, and the combustion chamber itself will actually constrain how much you can recirculate inside the burner. This is very simple. The larger the volume, the larger will be the possibility of recirculating exhaust gases. So what happens, in fact, if you use the same furnace that was, of course, developed for natural gas, and now we inject hydrogen? So what I'm looking at here is I'm actually putting inside the furnace at different axial locations a suction probe to measure the temperature. So what you see here are radial cuts at different axial locations. So you see with methane, you have a really flat temperature profile. Everything is distributed. You see that this promise of having a system that is completely diluted and where temperature increases very slight is fulfilled. Now, if I look at hydrogen in the same system, you are not working in flameless conditions anymore. You have a very significant temperatures. You reach almost 2000 Kelvin. And you see that there is a very strong rise of temperature. So the system, despite using a flameless furnace or a flameless, let's say, burner, is not working in flameless conditions. And so this is also visible if you do chemiluminescence. So you basically look at the spontaneous emissions from the flame. You see that in the methane, so this would be the exit of the burner at this stage here. And we actually record the emissions from the flame, and we realize that here the flame is shifted. Let's say the reaction region is shifted downward, downstream, and it's largely distributed. So you see this volumetric distribution. So we say that this is a chemistry-controlled regime, and if you want to talk about non-dimensional numbers, the Dunn-Kohler number is low here because it means that chemistry and fluid mechanics timescales are of the same order of magnitude. Now, if I work with hydrogen, you see that the flame is almost attached to the burner. Actually, we don't even know because the first window we have is 100 millimeters above the nozzle exit. So we can see just this, and we see that, in fact, it's fully attached. Now, what happens to the NOx? Do we have still single-digit NOx? What do you think? No. This is how NOx will behave with hydrogen. So you see that they would increase and would reach, this is, close to 1-2 ppm that we have with methane. We reach up to almost 200 ppm of NOx. But then you see also two curves. And so one is with a certain injector, the other one with another injector. So this is the nominal diameter of the injector. You see that if I decrease the size of the injector, I have smaller or lower emissions of nitrogen oxides. And this can be explained by the fact that if you increase the speed, so if you decrease the size of the injector, you you're actually increasing the speed of the fuel issuing inside the furnace. So you're making mixing more effective. And so you are actively reducing the downcoder number of the system, okay? And so you actually see that by doing this, you are already saving a lot of NOx. Is this enough? Maybe. We tried to go farther. And so what we did was to say, okay, let's think about how we can still make the process more slower, in the sense to make the two processes competitive with respect to each other. And so what we did was to say, if we design a new injector for the fuel, we can actively delay the time or the location where the fresh reactants will meet with the exhaust gases and react, right? And so what we did was to actually design an injection lance for the fuel that is actually 50 millimeters longer. And you see that by doing this, you lower you actually halve your NOx by going from 60 to 30. So still you don't have the single digit, but you can reduce from 200 to almost 30 ppm, which is a big step. So I think this demonstrates clearly that flameless is not an absolute concept. It's not a universal concept. I want to talk about ammonia now, and I have two examples. So up to now, you understood why we would use ammonia as a hydrogen carrier, because it's easier in terms of storage per unit volume. What we said as well is that the flammability limits are actually narrow. The flame speed is actually very low. We have a low adiabatic flame temperature, and we have high NOx. Also because we have nitrogen now that is bonded to the fuel itself. So we cannot get rid of this. So controlling nitrogen oxides here is very, very tricky, and flameless combustion could be a very good solution here because of its volumetric, let's say, kind of features. So to actually burn ammonia, we have different possibilities to look at. We could actually improve the reactivity by using oxyfuel or by introducing hydrogen with ammonia. We could do partial or total ammonia cracking. This would actually produce in situ H2. We could also do stage combustion, and then we talk about this. Now, this work has been presented in this paper, so if you're interested, you can actually look at the source for more information. Mariana, the first author, is actually working now in Hagen with Professor Heinz Pitsch, so he's actually close to here. So in this case, we actually performed a very extensive campaign. What we wanted to actually check was whether we could burn or we could demonstrate flameless combustion with ammonia in a wide range of conditions. What we did was to actually use oxyfuel conditions. So we have a range of oxygen in the oxidizer. Sorry. From standard air conditions, 21% to 50%. And then you see all the other parameters. But let me highlight a little bit the most important results. So first thing that we see is that we were able to actually achieve stable ammonia combustion at minimum enrichment of 30% in flame mode, whereas in flameless combustion or mild combustion, we had to go a little bit higher, so 34%. And this was the first time we were able to stabilize mild combustion of pure ammonia. In the past, the only way we could actually achieve that was to use, for instance, a certain percentage of hydrogen inside the fuel. So let's say 5% of hydrogen. What you actually see here is that there is a significant difference in the flame appearance between the two modes. Of course, in flame, you see a flame. In flameless, you don't see any flame. And you also see that for the flame, for the different conditions that you have, which correspond to actually different equivalence ratio, the appearance of this reaction region changes. Now, when it comes to, I mean, you can quantify this a little bit better by looking at the temperature profile. you do realize here that in flame condition I have some significant gradients. This can be also at the origin of higher NOx emissions, as we will see. And if I go in flameless conditions, I really have a very, very well distributed reaction zone and temperature. So the system really evolves towards this volumetric regime. Now, this is a very dense slide. I will try to actually highlight the most important points. You see here again the temperatures, and what you see here are the emissions. Now, this is what we care about. I told you that ammonia is intrinsically the issue of having nitrogen bonded inside the fuel. It's NH3, right? So you expect to have high emissions. Now, the point is that what can you do to lower these emissions? And so you see that when you actually use standard flame conditions, you have a trade-off between ammonia slip and emissions of NOx that is located at very large values of both. So you see we are around 800 ppm. So why I talk about trade-off? Because of course you don't want to have very low emissions at the cost of emitting ammonia. Emitting ammonia in the exhaust would be even, I mean, it would not make any sense to not to say other things, right? So you would not be burning your fuel. Ammonia is regulated even more than nitrogen oxide. So you have to be, let's say, not producing any ammonia. So what you could do is that you could actually work on a trade-off and then use a post-combustion kind of system to convert the remaining ammonia. But what you see here is that this trade-off here is at very high concentration, whereas if you check the trade-off for flameless conditions, this is a log scale, then you are at much lower concentrations. So you see that the process itself is actually helping already a lot in reducing the potential emissions associated to the process, because you have some reactions of DNOx that happen because of the distribution of temperature and the volumetric regime. And to actually show how this can be very effective, I want to show the next work, which is about which actually is about the microgas turbine built by Metis, by Michel. And here we actually explored a potential of using staged combustion in order to have a combustion process with ammonia and very low emissions. So you see here, this is just thermodynamics, no combustion, no kinetics here at all. You see that there is actually this trade-off I was mentioning about between what you have with the ammonia emissions and the NOx emissions. You actually see that if you work in rich conditions, so let's say slightly higher than 115, let's say, you could have a minimum emissions for both of them. You would actually have some residual ammonia, which means that you cannot realize this process in only one step. You need a couple of steps to do that. But this actually gives some ideas how you can do this effectively, and we explored that in this other work. If you're interested, again, this is the full reference. The idea would be to actually make use of the two-stage design that was proposed by this burner by Metis, because the fact that it's already a two-stage design allows you to think of the combustion process in two phases. One where you burn in rich conditions, and then you have residual NOx and residual ammonia. And the second stage where you actually perform the oxidation of the residual ammonia, and you actually exploit the fact that you have ammonia and NOx at the same time to perform in situ selective non-catalytic reduction, so the reduction of NO by NH3. So the original design by Metis was to actually use a lean stage and the subsequent addition of air to complete the combustion in the second stage. What we actually explored was to perform this in 2 stages, but now we would have first a rich stage and then a second lean stage. So you see that in the first rich stage, we would be producing some NOx, and we will have some unburned ammonia. And then in the second stage, we would have, ideally, at the end, no ammonia and no NOx. So let's see if this works. So to see if this concept could even work, what we did was to start first with the existing burner, so the one that you see here that we call A-type. So you see that you have a certain split of primary and secondary air for the first and second stage, and then you have your exhaust gases. What we did here was to actually perform experiments and validate a numerical model to have a numerical model that could be explored for the numerical prototyping of the other configurations. Now, one point I want to clarify here that is actually very important is the chemical kinetics. So ammonia is a new fuel. There is a lot of uncertainties associated to its chemical kinetics. So it was really important to choose the correct chemical kinetic mechanism, and what we actually found to be the most effective was this mechanism by Shesta. And the one that was actually closer to the experiment and the NOx emissions that we were observing, as you see here, for different values of the equivalence ratio. Then what we did was to make two variations of this design. One that we call B-type, that is still a two-stage process where we do what we do is simply to actually lower this diameter to have more effective mixing in the first stage. And then we have a C-type kind of design where what we do is actually to introduce holes. In this case, 4 holes, but you could actually play with this number. We saw that there was not much difference after a certain number of holes. The idea is to have a gradual injection of air in the second stage so that the consumption of the residual ammonia is also gradual, and the consumption of the associated NOx emissions is also gradual. Okay, so let's see if this works. So what you see here is that with these two kind of variations, this one is very simply just reducing the diameter. This one is the introduction of the different holes of dilution. You see that we have a well-developed flame or combustion region. It's not really a flame. And we have a very good mixing. And what is more important here is that we have, going from this to this configuration, a very significant NOx decrease. I think this could be more clear if we look at the outlet from the different stages. So you see here for two different equivalence ratios, so 115, 145 of the first stage. So the overall phi is a lean equivalence ratio. So this is just the equivalence ratio in the first stage. You see how the ammonia and NOx behave. I would actually focus on these two. You see that we go from, we have a 91% reduction from 600 to 57 ppm for the C-type at 115. And we actually have 64% from 1,600 to, let's say, 580 ppm for the phi 1.45%, 1.45. Okay, so it's actually possible to burn ammonia. Sorry, I don't find the, okay. So what we actually found in this case was that it was actually possible to have very efficient, so meaning no ammonia, and low pollutant emissions, meaning here a small concentration of NOx, by bringing some small or minor modification to the initial geometry that we were provided with. What happens? Because maybe you wonder, but in reality, what is going on? I don't know. This is not working anymore.
Press on center, it doesn't work.
Mm-hmm.
Can we go to the next slide? Maybe you can just.
Yeah. Can you? Okay, so maybe you're wondering what is going on. So what I'm plotting here is the reaction rate of this reaction. So this reaction is a very important reaction in our case because this is the reaction that will consume the NOx that are formed in the second stage and that are actually coming out of the first stage, thanks to the ammonia that is actually available at the end of the first stage. So the ammonia will decompose, form the radical NH2. NH2 would react with NO to form N2. Okay? So what you see here is on the top what happens at phi1, so phi at the exit of this first stage 115 or phi1 145. You see that what happens with the different holes of this type C configuration is that you have each time the introduction of air, formation of NOx, and consumption of NOx locally. So this red spot that you see is the occurrence of this reaction that consumes NOx. Okay. Okay, so I don't know how much time I have still. Yeah, that's good. Maybe I just want to finish with a small discussion on how we can actually combine these numerical simulations that I discussed with experiments in order to develop what we call digital twins of these systems. We think it's very important for advancing the knowledge of new technologies with new fuels, and also to take decisions about the potential impact of these new fuels in terms of combustion process emissions, product quality, everything. If we have a combustion process, we can of course use experiments. Probably some of you use thermocouples, cameras. We can shoot lasers inside. Now, in a combustion process, it's difficult to do a lot of measurements because of the harsh environment. You can still do many, many things. But I would say because of the harsh environment, you are limited to a certain extent. We can do simulations, but of course, I would say that still today, what we call high-fidelity simulations are still unsuitable for practical combustion systems. So what we try to actually push in our lab is also this combination of experiments and simulations towards the development of digital twins. And to do that, we actually use and resort to machine learning techniques combined with the two. Maybe in the interest of time, I will just talk about the first approach, which is an approach where we actually combine a Fisher extraction method called proper orthogonal decomposition with some machine learning techniques to develop digital twins of combustion systems. And I will show an application to the furnace. So what is the idea here is that we have some physical system. It's our furnace. We can actually perform simulation of this system. And we have experiments. We have seen some of them. What we can do is that we can actually use those to perform some Fisher extraction to extract what we call the modes of the system. Now, the modes of the system will form what we call some physics invariant information about the system. And the coefficients of this composition will actually be what we call system-dependent information. So the information that will depend, for instance, on some scenario parameters that we have. So imagine that you are changing your injector size, you are changing your hydrogen content, you are changing your equivalence ratio, okay? So we can characterize a system in a large design space. We can develop these simulations, and then we can, with the approach that I was describing just in the picture here, we could say that any scalar field in my simulation or for my physical twin is the combination of some invariant modes and some coefficients. And so these coefficients, it's where machine learning plays a role. It's where we actually use these machine learning techniques. Now we have used this for our digital twin. You see here, for our furnace. You see here on the left a field that is actually obtained with CFD simulation. We see on the right a digital twin. They are not exactly the same. They're very close. What is most important to note is that the one on the left takes days or weeks with detailed chemistry, for instance. This is actually almost real time. Something that I wanted to point out, I don't know if there was a video here, but it's not running. Anyway, not a problem. What you would see here is that the range of conditions that this model can capture is very wide, because it goes from fuel methane combustion, so very smooth distributed combustion process, up to hydrogen combustion. So you have a big delta T inside the furnace that is model is able to capture. What I'm saying is that this model is not capturing one condition. It's capturing the condition that are associated to this entire design space, where I go from 0 to 100% hydrogen. And the change in the fuel actually is a big change for the model. The errors are actually very interesting. So you see here what would be the error as I start removing simulations from the model. This is called left out analysis, left one out, or left out analysis of the model. What you see is that if I'm interested in some integral properties, or for instance the wall temperature, the length of the flame, the position of the peak of OH, that would be for instance the position of the flame, I have very good error in the range of a few percent. Now if I am interested in a specific property, like how much is the peak of a species, of course I have higher error, but still I am in the range of 10%, which is for a model that takes a second, I think very good. Again, there was here a video. I don't know why it's not running, but anyway, this was actually showing what you can do with this. For instance, if you are anticipating a variation of H2 in your charge, you can actually, you would see this animating and see how the temperature field will actually change. Now, the next and last question is, now this model is kind of a virtual shadow of your system. Can I actually use it and continuously update it as I get more information from my system? Because of course, if you have a furnace, you will still collect some data on the furnace. You have, I don't know, a thermocouple somewhere, and so you can actually use this information to improve your model continuously. And this is what we have done. The idea is very simple, that we have some experiments, and so this machine learning part can be continuously updated, because I have actually experiments coming from the furnace. And this is what you see here. This is the original digital twin. This is the error, so CFD versus experiments, and this is the updated digital twin once I perform this process of data assimilation. So this is a typical, I mean, very well-known technique in control theory, for instance. So you perform data assimilation, so it means you assimilate two different sources of information for the same process with their respective uncertainties, and so you can build a model with higher trust. Okay, so with that I will close, so there is time for discussion. Let me jump to this. Concluding remarks. So maybe the 4 things I wanted you to retain is that mild combustion or flameless combustion, you always have to look at the overall process, so fuel, burner, furnace. Now we showed that you can actually do stable mild combustion of ammonia, but NOx emissions are still a problem, because ammonia contains contains this nitrogen bonded to the fuel. You could do some low emission ammonia, but you have to now think about a more advanced configurations, and so staging is a real promising technique. And finally, that you could actually, there is a problem here. I don't know why it's doubled 2 times the same, but the 4th one was that you can actually combine experiment simulations to develop this virtual replica, these digital twins of complex combustion systems. Okay, with that, I would thank you for the attention.
So I see that there are questions directly, but maybe we need to pass the mic on.
So thank you, Alessandro. It was very, very interesting. It even convinced me that I should try ammonia. We should try ammonia combustion. So no, it's very nice, very, very interesting presentations. I have a question on the digital twin. So what I understand is that you're extracting the modes from this PCA analysis. This one is purely based on simulation, I guess.
Yeah.
And then the experiments you can feed in through the machine learning for the coefficient. So how many simulation do you need actually for like a certain number of variables for the PCA based on the simulation?
So we saw that, I suppose that you can hear me. You can hear me? Yeah. So in this specific case, we saw that, for instance, a design space filled with around 50 simulations was actually good for 3 input parameter space. Now there is not in statistics a clear rule about how many simulations you need. We usually rely on our experience, and I would say that there is this n+1 times n+2 times 2 rule that you should use to fill enough your design space. But of course, this also depends on how complex is your system. And so what we are actually doing now is to work on something that we call multi-fidelity digital twins, where we realize that maybe performing 3D CFD simulations of like 50, hundreds of them, it's not possible. And so what you can do is that you can perform a lot of, for instance, 0D, 1D, 2D simulations, some 3D, and then combining the two with different level of fidelities, you can actually get your model. So there are techniques to do multi-fidelity assimilation, it's called, and we are actually working on that because you want to reduce the overhead associated to how many simulations you have to run for your digital twin. Yeah.
Yeah, thank you for such a good presentation. I also had a question on the digital twin. So you use POD method for feature extraction. And the first matrix in there gives the pattern distribution of the flame, for example. So you base that on the data set of the CFD simulations, right? Because in the real system, it would be very difficult to extract data, if I'm correct.
Yeah, a very good point. So we actually use the simulations because we want to have a full digital model of the entire furnace. And then the modes are extracted, as you say, from the simulations, but then this model is evolving because you are simulating experiments from the real furnace. And so even if you actually assimilate all the experiments for temperature, you're actually changing all the fields, not only temperature.
Yeah, maybe I have two short questions. One is on the graph you showed on ammonia combustion as a function of oxygen. Probably I misunderstood that graph, but you said unstable combustion below something like 30%. Then my conclusion would be you cannot burn ammonia with air. Is that a stupid conclusion?
No, it's yes and no. It's a bit more complicated in the sense that this also depends on the heat losses of your system, right? So in our system, so you have some heat losses that make mild combustion of ammonia unsustainable below that enrichment. But if you were to actually contain more your heat losses, maybe you manage to do that with a lower oxygen enrichment. But now also take into account that in many furnaces you have significant heat losses because the heat loss is what you want to do. You want to transfer heat to a charge, for instance, a material. So the heat loss is a key part of the process itself. So in our case, we have heat losses around 40% of the input.
One other question is nowadays you hear a lot about using ammonia in the marine sector and shipping. You have a lot of experience with combustion of ammonia. Is it a smart idea, or does it give a lot of problems?
So there are already engines, as far as I know, that work with ammonia and have been demonstrated. So but this is a very biased opinion. I wouldn't burn ammonia. This is my personal opinion. But if in that case, maybe it's actually justified because you cannot do otherwise. You cannot use hydrogen. The other alternative could be to actually work on a tailored synthetic biofuel. This could be probably a better idea. Also because if you start looking at how much hydrogen you have to produce to actually satisfy the maritime sector, the steel sector, the glass sector, then you get quantities that are just impossible. And so maybe what we should do is really prioritize the fields. Maybe the first one should be ammonia production. So ammonia for agriculture, I mean, because ammonia, we use it a lot for agriculture already. Or then we should do for steel, and then maybe we should not do hydrogen for domestic heat, for instance.
Marine has a very strong decarbonization target.
Yeah, I know.
2030 they have to already reach.
Yeah, no, but maybe they.
2050 they have to be.
And then you have a strong enox target afterwards.
But they have already.
But since the engine is so big, so you know it's huge, the engine of then maybe they can also easily accommodate a post NOx treatment system. So it's easier than in a car. That's what I mean. Yeah,
Thank you, Alessandro. It was a great presentation. I have a question related with the digital twin first, which is you are doing the POD with the like how many variables do you extract to make the PODs? Like temperature, pressure, velocity, everything. And also OH?
Yeah, all the fields
Okay.
that we have available.
Okay. And the second is a small question. Like I see that in your charts you are showing NOx, for example, at 3% oxygen. Why 3%? Is like a reference in the industry or?
Yeah, 3% is a reference in furnaces.
Okay.
Because
Thanks.
they use 16% in general excise there. There was one there or, to the back.
Hello. Yes, thank you for your nice presentation. So I want to just ask you regarding this fuel injection. You see, I mean, you are showing that this nozzle, you know, the fuel nozzle, you increased it. So when we do these simulations, actually, for example, for the hydrogen methane mixtures, for example, we always see that the hydrogen is easily eating up the oxygen atoms. Actually, oxygen is oxidizing faster and is accelerating. And then there's a lot of high temperature, and thereby you see we have a high NOx. For example, the methane hydrogen mixtures. So do you think this kind of pushing forward this kind of fuels, for example, mixture, because you have different OH fractions. For example, the hydrogen is burning at some point of your flame tube, and the other one is burning on for example, the methane is more burning far apart because they are doing it differently. So do you think this kind of fuel, you know, putting the fuel a little bit, positioning it, the fuel inlet positioning, does it help for this kind of mixtures?
I mean, okay.
Yeah, you know.
This one?
Yeah, this, yes.
Yeah, so now let me go here. So to actually work in flameless combustion, let's see.
Maybe you can use the mic.
Yeah, thanks. So to work with flameless combustion, so you need to be sure that combustion process happens after reactants have met the flue gases, right? Because otherwise you are actually just burning the reactants with the fuel with the fresh oxidizer. Huh? So you want to first dilute the oxidizer with the exhaust and then make the reaction occur. So this strategy here is simply to reach this kind of result, because if I increase the length of the injection system of the fuel, what will happen is that my oxidizer that is coming up from here will first meet the exhaust gases a little bit before meets the fuel. And so I'm delaying or like I'm allowing to have mixing between exhaust gases and oxidizer before meeting the fuel. And this is necessary because hydrogen is very reactive. With the methane, it was not an issue because ammonia has a higher ignition delay time, and so regardless of the fact that this was not as long, it was still taking first, mixing was still taking first place before the reaction took place.
So what you show when you do this, actually, it's experimental results on the right, yes?
Yeah, yeah.
Because it's funny, because what we would do is reduce the diameter of your injector so that we push the hydrogen faster.
But you could do both, right? So this is reducing the diameter.
Ah, yeah, okay, okay.
And then in addition to that, you also reduce.
Yeah, I see.
So it's both. It's also what you say. Yeah?
So ammonia, as you said, is difficult to burn, right? And it also has a comparatively lower heating value. So you need to put in more ammonia for achieving higher power at the end. So the ignition system, and there are strong regulations for ammonia that go out. So if it comes unburnt, then how precise must the ignition systems be? And do we have such systems available? That was my first question, and second was about the digital twin again.
Yes, so we can't afford any ammonia slip, in fact, because even 10 ppm is a lot with ammonia. So in any case, I think ignition will not be a problem. You can have ignition which is assisted somehow, even with the fuel, with the blend. The problem will be that most of these systems, my point of view is that there will be a post-combustion kind of region, and so this makes the volumes a bit larger and so on. Or it should be a compact design like the one of Metis, where you have the two stages combined. Thank you.
Thank you so much for the presentation, also for the wonderful discussion. I think we'll have to continue with the discussion in the break now. But I do have one question online about the Fit for Micro project. So the question is, which AI tools are going to be used for optimization? So Michelle, can you take that? Which AI tools are going to be used for optimization for the system?
AI?
Yeah.
We're not using
It was in this presentation.
Oh, okay. But it was in both presentations, I thought.
No, it's in the Alessandro.
Ah, okay. No,
Machine learning suite.
it was given even before the presentation started, so I thought it was for the Fit for Micro.
Well, we're not really using any
So we use our tools. We develop in.
Yeah, maybe you can. I got the question twice.
Yeah. So we have our software. I didn't put the slide to the, but it's available on our research page. It's basically codes we develop in Python and other languages. So the page is on. I can put it after on the chat. We have a page with all the software. It's on GitHub.
Perfect. Thank you so much. And now we break for coffee. We'll come back in 15 minutes. For the online attendees, we'll come back in 15 minutes. See you on the other side. Thank you.
Just like me, they long to be close to you. Just like me, they long to be close to you. Close to you.
Okay, welcome back after the coffee break. Also, hello to everyone joining online. Now we move to the details, or we're going to dive into the details of the technologies that make the Fit for Micro project. And we start from the starting. That's where we look at alternative energy sources from biomass, and Evert Leidenhorst is going to present the biofuels that will be used for this project.
Okay, thank you. Good afternoon. My name is Evert Leidenhorst. I work at BTG Biomass Technology Group in the Netherlands, and I would like to present our work on the production of biofuels from residues via fast pyrolysis and hydrotreatment. I will start with a very short introduction on the use of biomass residues, the opportunities and limitations associated with it. Then I will explain the fast pyrolysis process, where we produce a liquid bioenergy carrier from a solid biomass. I will discuss the hydrotreatment process, where we produce a drop-in biofuel. And I will conclude with some biofuel applications and some quality control measures. So very shortly, biomass residues. There are important opportunities. If you look at residues from food, feed, forestry processing, these are widely available. To put some numbers on it, in Europe alone there's over 123 million tons of oil equivalent, so basically the energy value of the biomass, which can be made available for the process route I'm discussing today. And made available means in this case there's no or low competitive use, and they're technically suitable for this route. These feedstocks, they comply with the Renewable Energy Directive, more specifically Annex 9 Part A. So basically this means any biofuel you produce from it can be qualified as an advanced biofuel. If you compare this, for example, to alternatives where biofuels are produced from oil residues, waste cooking oils, this availability is huge. However, there are also some limitations in using biomass residues. Of course, there's a very large variation. If you consider forest residues or straw or bark or corn stover, these are very different types of materials, both in physical structure, the density, the fibrous nature, also the biochemical composition. They have different cellulose, hemicellulose, lignin contents, but also the ash composition is very, very important in processing. Ultimately, if you want to use this resource, you want to have a flexible process, something which can take in different types of biomasses. The second important limitation is that these residues, they are usually available in decentralized or rural locations. So there's a mismatch between the amount of biomass available and current oil refinery operations. But due to the low energy density, it's very difficult or impossible to transport these biomass residues over a large distance to a central processing unit. If you look at flexibility and operational cost, we do, however, have to use some sort of minimum scale. So to have one installation going through all the different agricultural fields will also be challenging from an economic point of view. So that's why we focus on a medium scale pre-conversion. With those limitations and opportunities in mind, the approach we are following is to have a spoke and hub system in which we deal with these challenges, where we first have the fast pyrolysis of the feedstock at a medium scale, so we're talking about 25 megawatts input more or less. Different biomass residues are converted to pyrolysis oil, or FPBO in short. And these FPBOs, they are sent to a centralized refinery where the hydrotreatment process is executed and the fast pyrolysis bio-oil is converted into a drop-in biofuel. This is also a nice match in the hydrotreatment process not only from an economy of scale, but also the type of infrastructure. So our hydrotreatment process, it's quite closely related to current oil refinery treatment processes. That's basically the concept. Now I would like to show in a bit more detail how the technologies work. First of all, we have the fast pyrolysis process, and in this process we produce what we call the liquid bioenergy carrier, FPBO, or fast pyrolysis bio oil. And basically fast pyrolysis is rapid heating in an oxygen-free atmosphere. So you have a thermal decomposition of your biomass. The biomass you feed into the reactor, there is mixed with hot sand from the combustor. This initiates pyrolysis vapors, and they are condensed with an oil spray. And after that you get the liquid pyrolysis oil as a main product. There's also a byproduct in the form of non-condensable gas removed from the condenser. And in the reactor you also have a second byproduct, which is a char, a solid remainder. And this char is sent to the char combustor, where it's combusted to generate the heat required for the process. The only other thing you get from the process is the ash. As I mentioned, this process is feedstock flexible, so it works with clean wood, it works with bark, it works with grass, it works with straw, all these kinds of materials. You can have relatively high liquid yields, up to 70%. You don't need any external energy for the system, you don't need any chemicals for processing, and you don't generate any waste. And because of these advantages, it's economically feasible at medium scale. So yeah, because it's self-sustaining and relatively simple processing, you are able to do it at 25 megawatt. If we talk about the status of the technology, the fast pyrolysis production reached TRL 9. So our sister company, they already developed 3 commercial scale installations in Europe. You can order the FPBO in a web shop. You can order your own pyrolysis plant if you want. So the technology is there. What we are doing at BTG and also in this project is we are more developing or working on the hydrotreatment technology. So the properties of the pyrolysis oil I haven't mentioned yet, but it's in the blue box in the middle. That's why we call it a liquid bioenergy carrier. It's not yet an oil. It contains water, it has a high density, low heating value, it's acidic, and also if you distill it, that's the bottom part, the MCRT, it's a carbon residue, so you cannot evaporate everything. What we are doing in Fit for Micro project, amongst others, is to upgrade it to a hydrotreated pyrolysis oil. Is this needed? Maybe not, maybe yes. You can use the fast pyrolysis oil directly as a fuel for heat and power production, for example, but then you have to modify the system. So we've done research in an internal combustion engine, and then you modify the engine to be able to run on pyrolysis oil. Also, what you can do is you can co-process FPBO directly in an oil refinery, but then only at very low blend levels. So in this case, what we propose to do is upgrade the oil quality by hydrotreatment. And this should allow the use of the FPBO in, for example, a micro gas turbine for small scale CCHP. Or also, if you upgrade further, you can even use it as an advanced biofuel in the transport sector, produce renewable gasoline, kerosene, diesel-like fractions. The process, we do it in 2 stages. Basically, it's the reaction of the FPBO with hydrogen at elevated temperature and pressure. You're talking about 100, 200 bars, 200, 300, 400 degrees centigrade, so quite severe reaction conditions. And if you do it in 2 stages, you first stabilize the pyrolysis oil and then you hydrogenate it. I make this distinction because we use 2 different catalysts. And the catalyst in the first reactor, this is the very important one, and this is also where the knowledge of BTG is. And basically the second stage, it's closer to the oil refinery already, so there we use conventional hydrotreatment catalysts. And what is nice about the processing is the quality of the product can be steered with the operating conditions. Generally, the more hydrogen you put in, the better your fuel quality will be. But of course, the more hydrogen you put in, the higher your fuel cost will be. We have several research installations. So the pyrolysis oil production is commercial. This one is not yet commercial. I would estimate the technology readiness level 4 or 5. We have 4 or 5 bench scale hydrotreaters at PTG, which are able to run continuously and produce around 1 kilogram a day of fuel, and 1 pilot scale hydrotreater, which is run during the weekdays and produces around 50 kilograms a day. And with this one, we make samples, we test different operating conditions. We've done this in different projects, also commercial testing. In the Fit for Micro project, we're looking mainly at reducing fuel cost. So not adding as much hydrogen as possible, but rather limiting it and making sure we produce a fuel which is just good enough for the micro gas turbine. In the graph you can see a way where we try to pinpoint different fuel qualities. We listed it as a function of the total hydrogen content in the fuel and the hydrogen over carbon ratio. And basically we find that the more processing we do, the higher the quality becomes. On the right hand side you can see image of some of the fuel qualities where, let's see, I mentioned this. So the Fit for Micro region is, I think it should be a little bit more probably over here, misplaced in the sheet. What we've used up till now is the reference quality HPO, which is this one, and this is the center part somewhere over here. And now we're trying to reduce the quality while still making sure fuel is properly combusted. The first results of the project, they indicate that this reference quality is already suitable for use in the microgas turbine. We produced a few hundred liters so far, available for the project already. So this is very good and promising initial results. We are now doing some testing to reduce the severity and reduce the production cost while maintaining a suitable fuel quality. Of course, complying with the emission regulations. The other thing which I would like to mention today is if we go to a very high severely treated product, this is a way to produce a sustainable aviation fuel, or a SAF, and also a road diesel function. Even if you have these high severity treatment processes, you will always have byproducts. These byproducts, they can be considered for the microgas turbine uses as well. And in this sense, it's really starting to look like a conventional refinery where you have different products from one entering feed stream. And I think for our biorefinery approach, it will be a similar scenario where we start with pyrolysis oil and then make a range of different products which can be used for a range of different applications. So there's very quickly an overview of the work we've been doing. To summarize, biomass residues, they are widely available and they provide a renewable resource for biofuel production. If you apply fast pyrolysis followed by hydrotreatment, this is a way to overcome the typical limitations of the biomass residues. So you're able to deal with the variable composition because of the flexible pre-processing, and you're able to solve the logistic issues, basically connecting the agricultural rural environment to the conventional oil refinery scale. Finally, you can produce various fuel qualities. So depending on your need, you tailor the process, of course trying to limit the fuel production cost for the specific applications. With that, I would like to conclude. Thank you.
Thank you so much, Ebert. Are there questions? Yes. We'll come to you.
Thank you for the presentation. I was wondering, what is today the time that the SAF requires to be certified and used, for instance, in an airplane or?
The time between you start the procedure.
Yeah, I mean the time between when you realize it's a good fuel and then when they allow you to actually use it.
I'm not sure. Maybe Bert wants to comment on it.
Well, I don't think there is a straight answer because it depends also on how much testing you have to do. And I think at first, let's say tier 1, tier 2, it takes you 1.5, 2 years probably, and then it depends on what you have to do or what they decide you have to do in addition. So it might be, in an optimistic way, it might be 1.5 year, but might also be 4 years or 5 years. So it's very hard to give an answer to that.
Okay, thanks.
And we have a question online. Is the pyrolysis gas going to be used also in the production process?
Yes, for now we use it for energy recovery, so it's combusted. Of course, we're looking at higher value applications, but this is also research in progress. For now, it's combusted to limit emissions and recover the energy. Yeah.
Okay, but it's not part of the Fit for Micro project?
No, it's not part of the Fit for Micro. The scheme I showed is from a research installation. In the commercial plant, the gas goes to the char combustor, and there's heat recovery around it. Yeah.
Thank you.
Yes, so Yvette, so you say that so the FPBU you have used already into a piston engine.
Yeah.
And it's working properly, I guess. Because but so why not using it directly into the gas turbine? Because if it's working in the piston engine, I don't see why we could not use in the gas turbine.
It was working, but it's very challenging. So I think you have to redesign the injection system.
Yeah, well, it's
But also the start-stop is quite difficult. We have to have, now we have different fuels for startup and shutdown, racing fuels and ignition fuels. So
Okay.
it's rather complex for, I would say, small-scale applications. For large-scale, it can be done. Running a gas turbine on pyrolysis oil can be done, but micro-scale, I think it's probably a step too far.
okay. I'd like to try.
But yeah, if you like to try, we can always supply pyrolysis oil. No problem.
And we guarantee it's flameless.
We have more questions online?
Not combustion, but flameless.
So there is a question about hydro treatment, that it's an energy intensive process. What is the ratio of input to output in terms of energy? Maybe also you can talk about economics, because
I cannot talk about economics in detail. I can talk about energy. The energy recovery is quite high. If we go from the original biomass to the final HPO product, it's around 40–45% is recovered.
And another question about hydrotreatment with pyrolysis oil. Do you see reactor clogging, and how difficult is the process? Do you see remains and?
But this is the result of years of development work. So when we started, the reactor clogged a lot of times. We opened it up a lot of times. But now after development, and the key issue is controlling the conditions, but also having the right catalyst. So together with partners, we developed a very specific catalyst, which is able to overcome these issues. But if you start today, definitely you will have clogging, and yeah.
Maybe they can contact you for expertise.
They can always contact us.
Yeah. Okay. Is there another question here? And we have one more question online. Why have you tried using sugarcane bagasse as base material? And
We tried.
what's your experience with that?
It works surprisingly well. Yeah. The sugarcane, it gives a nice quality pyrolysis oil. Yeah,
Okay.
it works.
And what is the what is the difference or advantage over making pyrolysis oil over ethanol with sugarcane?
Yeah, it's much simpler. The efficiency will be much higher. We can get to 78% of pyrolysis oil out of the sugarcane, and with ethanol it will be much lower.
Okay.
Yeah. But of course, the ethanol is a nicer product to start with. Yeah. It's a trade-off. Yeah.
Okay, then thank you so much, Hayward, and let's move on to the next part of the process. The actual burning of the fuels. So the next topic is biofuels for combustion applications and the research efforts at OV. Dirk Muntman, my colleague, will be presenting it. The floor is yours. You can speak. Yes. This is the next slide. This is the previous slide. This is for the pointer. And you can just stop from here. I think it will catch it.
Okay. So, good afternoon, everybody. I will present a little bit about research efforts at OWI with biofuels for combustion applications. And I will start my presentation with a timeline of projects we had in the past, from the beginning till now, and I will introduce some fuels we have tested at OVE, and I will present some special fuel properties, and also some selected results from. Can't you hear me?
No,
And I will also present some selected results from the combustion, and I will close my presentation with a summary and an outlook. The first projects started with optimization of burners for domestic applications. That was for combustion of domestic heating oil. The challenges was the reduction of the emission from CO, residual hydrocarbons, and for NOx emissions. In 2001, the sulfur content was reduced for the domestic heating oil, or was limited to 1000 ppm for standard domestic heating oil, and low sulfur domestic heating oil was introduced with a maximum of 50 ppm. And it was found out that the low sulfur heating oil leads to less residues in the combustion chamber. The first biofuel was fatty acid methyl ester, and the first project was the investigation of deposition formation in pre-mixed combustion furnaces, and after that, in 2010, the plant for the production of hydrogenated vegetable oil from And in 2011, we had a project that was Flex-3. That was a construction of a modulating burner that was for fossil fuels and biofuels also. And the power range should be from 7 kilowatt to 15 kilowatt. And the intention was to follow the heat demand of a building. In 2015, we had the first project with fast produces bio-oil. That was residue to heat. That was the introduction of FPBO to the market of the domestic heating. And next project was started in 2019. That was a smart CHP. There was a FPBO fueled engine, and also post-combustion, the exhaust gas of the engine to increase the heat release from the system. And nowadays we have the Fit for Micro project, and our task is the combustion of HPO in
combustion chamber under pressure. For the combustion of liquid fuels, it is mandatory to have a good mixture formation, and under ideal conditions, the mixture formation is separated from the combustion. Then you achieve low emissions. And for the mixture formations, it is mandatory to atomize the fuel for best evaporation. You will see some liquids we handled with. That was former domestic heating oil, hydrogenated vegetable oil, APO, that is an pyrolysis oil from scrap tires. It was a byproduct of the production of carbon black. And we also handled distillation residues. That was left over from the production of polymers, and we also had a residue from the used cooking oil methyl ester production. And then in 2015 we had the FPBO, and nowadays we have several batches from hydrogenated pyrolysis bio-oil. If you want to characterize a fuel, we normally does it if we compare it to existing fuels on the market, and our norm is the norm for domestic heating oil, and there are some values given like density and kinematic viscosity, which are very important for the atomization of a fuel. Here we see some samples from HPO and HAL. We see the dynamic viscosity plotted over the temperature, and the results from HPO are very near to that from domestic heating oil for the dynamic viscosity and also for the density. Another characterization is thermographic analysis. Here we see a thermographic analysis from domestic heating oil and also for a HPO sample, and the HPO sample was evaporated in a crucible, and we measure the loss of weight, and we can see around about 230 degrees the domestic heating oil is going fully into the vapor phase, and the HPO is also fully in the vapor phase at 270 degrees, and half of the sample is always gone, so at 150 degrees for domestic heating oil and also for HPO. That is another example. The black line we see is the scrap tire oil from scrap tire pyrolysis oil. And what could happen, or what happens, we see a mass loss continuously until 20%. Then the evaporation stops and starts again at higher temperature at around about 220 degrees and ends at 500 degrees. And what happens there? It is the formation of higher residual carbons, and it's more difficulty to get them into the vapor phase. Next characterization is a so-called single drop evaporator. if you want to know what happens if a fuel is in contact with a hot or cold surface, that could happen if, for example, a droplet is drawn back by the flow or touch the flame tube. And we see some samples, the one for the distillation residue at the bottom, and you need a temperature around about 500 degrees to put it into the vapor phase with nearly no residues, and Okome used cooking oil methyl ester residue was going to the vapor phase at 300 degrees. Here we are at the residue to heat project. That was the application of a burner which is suitable for FPBO, and we applied it to a condensing boiler and with a 20 kilowatts thermal output. That was properly working. We had stable combustion results and low CO emissions. And what you can see here, the brown coating on the heat exchanger surface, it comes from ash formers, which are still in the FPBO. And within the Smart CHP project, we did a measurement with a cascade impactor, which is able to measure particle diameters from 10 microns down to 0.06 microns in 14 cascades. And there's no limitation for oil burners, for particulate matters or for dust. But in Germany, there's only the Federal Emission Act in stage 2. That is for single room furnaces. And there's a limitation of 40 milligram per cubic meter exhaust gas in total. That's a comparison to domestic heating oil. And with domestic heating oil and also with hydrogenated vegetable oil, and I would expect also with HPO, we are close to the detection limit with what we can measure with this technique. There are some challenges left. We've seen extreme pump wear, and the FPBO tends to varnish if it comes in contact with oxygen. That leads to clogging of nozzle and clogging of pumps if they are shut off for a longer time. And on the picture on the right side, we see extreme pump wear. It's a linear on it, and this slit leads to internal losses, pressure losses. The fuel is going from the pressure side to the suction side of the wheel, and the pump is no more able to achieve the necessary pressure for atomization. Now we are at the Fit for Micro project, and our task is the experimental validation of the combustor performance. We try to achieve a mild combustion, and this combustion chamber is HPO fueled, and the pressure will be up to 3.5 and 7 bars, and we want to achieve low NOx emissions and very low no CO emissions and very low NOx emissions. So here we are within the project, and back to the atomization. We've made a spray angle detection with the first design of a metis to substance nozzle. And here you can see pictures from that test with a mass flow of fuel, 5 kilograms per hour, and we varied the atomization air from 50 to 90 SLM. And we've made this picture in a photo box, and we want to investigate the spray angle, and we did it first very simple by printing a picture and measure it with a triangle, and next step we measured it with a software which is able to detect dark and light, the dark and light border. And for the mass flow of 5 kilograms, the spray angle keeps nearly constant over the variation of the atomizing air. And for a mass flow of 3 kilogram, it is varying between 25 degrees and 40 degrees. Then we did some particle size analysis at the OLB. That is a result, that is an example from the first metis design. And normally we see a proper Gaussian deviation of particle size. And here we have a deviation with 3 maxima. And then we designed a new nozzle, and this nozzle we also tested at the ULB. And nowadays we have a nearly proper spray characteristic, and with a mean sorted diameter of 25, around about 25 microns. So the summary, the combustion properties of HPO are very close to that of domestic heating oil, what we found so far. So it has no tendency to varnish. We have no pump wear. We have detected no pump wear or clogging or something like that, or filter blocking. And in the future, next task will be the minimization of a degree of the hydration, and we will test our combustion chamber at next with a second design metis nozzle, and we will perform pressure tests under pressure. So thank you for your attention. Question?
Thank you, Dirk. It was nice presentation. So, I mean, so the test you have already conducted with HPO and with our combustor was with the first design of the nozzle, and it was already quite not bad, let's say. So, even though we had this zone of relatively big particles, let's say, we see it in the spray. So, what do you expect actually when we have the second nozzle? Let's say, what will be the impact? It's on efficiency or something like this? Did we have soot or something like this when we were burning? Did you check?
We didn't check soot. I don't expect soot. for a suit measurement or a particle measurement, it would the equipment must run 3 or 5 hours, and we don't have so much fuel samples to do that. One measurement we couldn't do is it's a so-called it's a gray scala, Bacharach gray scala. One probe is sucked through a paper, and the paper is correlated to a gray scala, and you see it's a number, suit number 1, 2, or 3, or whatever. But I don't expect suit. So we don't see CO, we don't see suit.
Even at the start.
Pardon?
Even at start ignition.
We haven't done start measurements yet.
So you always have.
Start measurements are a problem. You always have a huge peak, which is higher than the limit of your measurement device. It's a little bit critical. More questions? No? Then I will give back to Ziri or Sangeeta.
Thank you. Thank you, Dave. Next, we have Danish Rahman, and the topic of his presentation is gas foil bearings for small-scale turbo machinery.
Thank you, Sangeeta. So which one does what?
Both of them work now.
Okay. So yes, hello everybody, and also the online audience. I'm here to present you a very complex topic. Mic. Now it's clear, right? Okay. So yeah, okay. So I'm here to present you a complex topic, but I will try to dumb it down such that I can communicate my message. But if it gets too detailed, please, we can discuss it afterwards. I am Danish, as introduced. I'm working as a R&D team lead in MITIS. MITIS, in context of Fit for Micro, is responsible for developing and testing the innovative two-stage cycle that is being discussed by Michel and other colleagues. So now when it comes to foil bearings, we have spent quite a lot of time developing the foil bearings. So we decided to give this specific talk based upon the foil bearings. To introduce you a little bit on the topic, I borrowed these slides directly from one of the forefathers of foil bearings, which is De La Corte from NASA Glenn Research Center. So here you see, for any rotating machinery, you need bearings. You need bearing system in order to reduce the friction when the shaft is rotating. So in general, when you look what kind of bearings are available, in the rotating machinery, you have rolling element bearings. That's the oldest, let's say, and the most conventional methodology. Then when it comes to gas turbine engines, we have plain journal bearings or tilted pad journal bearings, where there is oil in or lubrication being used in both rolling element bearings and plain element journal bearings. And then there are other type of bearings, which is, one is foil bearings and second is magnetic bearings, where you don't use oil. So they are oil-free bearings. Magnetic bearings work on a principle of magnetic levitation. So you levitate your shaft based given the magnetic field. And the foil bearings are self-lubricated bearings, which are very similar to plain journal bearings, but instead of using oil, you are using air film. So as the shaft rotates, it generates the pressure that it needs to lift off. So our focus will be on this talk on foil bearings. Another very important property of any bearing system is the load capacity of the bearing system. which is how much load they can carry when they rotate at a certain speed. So for conventional rolling element bearings, you see that as soon as you increase the shaft speed, as you start going this way, your load capacity of the bearing system reduces. But on the other hand, for the foil bearings, it actually increases with the speed. And when we are talking about the small scale turbo machinery, in general, you are rotating at much higher speeds. So we are talking of the speeds in 70,000 to 200,000 RPM, based upon the power that you want to generate. So when the size is small and you require good load capacity, the foil bearings are ideal. So with this introduction, as I said, the basic working principle that we have is that that you can see there that when the shaft rotates in a bearing housing, it generates the pressure to lift off, and you have a pressure bubble underneath, which is very similar to any journal bearing with oil. So instead of oil, you have air there, and the shaft generates enough pressure to levitate itself and then rotates freely. Here in this slide, you see different types of bearings. There are thrust bearings, of course, foil bearings, and the radial foil bearings. I will focus my work, or let's say this talk, for the sake of brevity, only on the radial foil bearings. There are different type of foil bearings when it comes to generation of the foil bearings. Here you can see on the right, you have bump foil bearings, in which you have a structure which is like a bump foil underneath a top foil. So the shaft transmits all the forces to the top foil, and then it gets transmitted to the bottom bump foil, and this gets dissipated as a heat to the structure of the sleeve. Here you have another way of having the bump foil. It's called beams, or let's say cantilever-based foils. So the advantages that we have of these bearings, of course, as I mentioned, you don't need oil. There is no restriction of the load capacity. The higher the speed, you increase the load capacity. And there is another thing very important, which is like no restriction of the dn number. It's again related with the speed. dn means diameter into n is the rotation speed. So in general, you want to have, when you go at higher speeds, your dn number increases, and where the other bearings do not support you well enough, so foil bearings come into play. Now, I have given you a little bit of perspective of foil bearings. Now, let's see how do we apply this to microturbines, or let's say a small-scale turbo machinery. So here, what I have is what I will refer to as preliminary sizing. Let's say, how do you take all of what we described earlier, like how do we design foil bearings for a small-scale turbo machinery? So in general, you will always start with a cycle analysis. Cycle analysis is based upon, okay, how much power do you want to generate? You will extract certain mass flow, certain pressure ratio. This will define your mass flow and pressure ratio, which will go on a little bit detailed design of your, it's not detailed, let's say preliminary analysis of your wheels, your rotor wheels, the size of the wheels, the weight of the wheels. So when you have defined this, based upon the results from the wheel's geometry and the optimum speed that you need for that wheel and the pressure ratio and the mass flow, you go on a preliminary bearing design, which according to a rule of thumb, you should have a DN between 3 million to 3.5 million, and based upon this, you extract your dimensions. So that's preliminary analysis. And afterwards, once you know the shaft diameter, the more complex analysis starts, where you have to know dynamic stiffness and dynamic coefficients of your bearing, as well as you have to conduct the rotor dynamic analysis to see the stability of the rotor and your bearing system. And of course, if there is something you have to improve, you need to look here. So there is a preliminary sizing and then a detailed analysis. I have given a lot so in this slide, so let's go step by step. Let's say if we want to design a cycle of 65 kilowatt electric power, how do we start? Given certain assumption on a very basic cycle, it's a recuperated gas turbine cycle, one can easily see that the cycle efficiency is improving with the increase in pressure ratio. That's quite generic. So always we want to have highest pressure, let's say highest cycle efficiency. which is happening at a very high pressure ratio. But given, let's say, the technological limitations, we cannot have a pressure ratio of 6 and also a good efficient wheels, let's say turbine in the compressor. So in general, we try to maximize our pressure ratio, given that we have efficient enough compressor and turbine of our turbo generator. So moving forward, once we know, let's say we set our pressure ratio as 4, where we have cycle efficiency still good enough, not decreased too much, and then we try to find out what is the good mass flow for our cycle. So let's say in this case it's 510 grams. You translate it to conventional charts of your turbo machine. You try to see an optimum design of your turbine, and finally, if you do a little bit of maths that I will not go in details, you can see that for a given size of the turbine, you will need a bearing of a size of 31 to 36 millimeter if we look at 3 million to 3.5 million DN that I mentioned earlier. So now let's say we have a preliminary size bearing. Moving forward, then it's the details where the things gets complicated. This is the test rig that we have developed at Metis, where you have a shaft. So this is to conduct step 4, which is static stiffness and your damping. What we do here, you have a shaft and a bearing, and then bearing is, you do not rotate your shaft, and then you apply certain force up and down on the bearing. So you move the bearing system up and down, and what it does, so this on the very right, sorry, yeah, but we can jump here, this is how it looks like. You have a bearing system into your sleeve mounted. What you do is you do a complete cycle of loading and unloading, and what it gives you a force and the deflection curve, which is shown here. So one curve is when you are loading the bearing, and then another curve for unloading the bearing. So that's called hysteresis curve. And the very reason, let's say, that we could damp vibration energy inside a bearing system is because of this hysteresis. Because the difference in the energy between the two curves is actually your damping energy. So let's say it's one of the, let's say, set of experiments that we conducted for multiple different configurations of the structure of the bearing. If you do analysis on multiple different foils structure, you will see that you have load deflection curves, which are different here for different types of bearings, and then you can generate also the stiffness curves for the same bearings from the data there. So of course you can, this is your F is equal to Kx, and if you derivate it, you will get the stiffness of the bearing itself, but that's static stiffness. And also the energy dissipated in the hysteresis loop, you can have a very good idea like how much energy is being damped and how stiff your bearings would be. But again, this is a static stiffness and damping, and we have to still look for other things which are important when it comes to the design of the foil bearing. Now, you have designed, let's say, or you have understood the structural properties a little bit of your bearing. Another very important stuff is to know when do you actually lift off, which means at what speed you have generated enough pressure that your shaft levitates. We typically do it with a Strebberg curve like this. It's the same test bench that I showed earlier, but now we rotate the shaft. We rotate the shaft by applying certain load on the bearing. Once we rotate the shaft, here we have rotated it up to 30,000 RPM. What you see here is the frictional torque, which means the resistance to the movement. So you see at the beginning, when we just want to start the rotation, you see a big peak or big rise in the torque. It means that it's resisting to move. And then as soon as the air film establishes, so here, for example, you're already at 30,000, 25,000, or whatever speed you're lifting off, your torque is minimum. And then you maintain this minimum torque for all the time that you're rotating. So this establishes that you are lifted off, and you have a very minimum torque. Minimum torque means that there is still friction, but you are at minimum power loss. So this is still heat generated that you need to dissipate when you are running your gas foil bearing. And similarly, I mean, from this torque we can get the power loss that's shown there for different designs of the bearings, we could see, okay, which combination of the top foil and the underspring gives us the minimum power loss. Because if you have a very high power loss, it means that you are overheating your bearing, and this can lead to problems and the, let's say, crash of your turbo system. Now, from this part, we have to know also the dynamic stiffness and damping. Why? Because the stiffness and the damping that you calculated earlier is not valid for all the speed. So your rotor actually moves from your 0 RPM to 100,000 or let's say 200,000 RPM, which reflects into, let's say, 1.5 to 2 kilohertz of frequency. So you need to know if the structural properties of the bearing are changing with the change in the frequency, which is the rotation frequency. In general, in any rotating machinery, the rotation frequency is your main frequency of vibrations. So this is why it's important to understand how the properties, structural properties of the bearing would change with this frequency. For this, there are two ways. One is the experimental that is shown here, in which what you do is that you attach your bearing again, you don't rotate the shaft, and you attach it with a stinger shaker. And then you shake it at a certain frequency. So you set the amplitude of vibration, and you also set the frequency of vibration. By doing this, you can repeat the same analysis that we did earlier of the stiffness and the damping, and you will extract like damping and the stiffness that is changing with your frequency. In general, we see that your stiffness is increasing with the frequency, and your damping is decreasing with the frequency. In general, it's very difficult to have a stinger shaker that can go up to 2 kilohertz without resonating a lot of other components in your test rig. So most of the experimental studies that we found in the literature are limited to a certain extent. So for example, this tells us 30,000 RPM or 40,000 RPM. But to know like properties at 3 kilohertz, 2 kilohertz, like 100,000, 200,000 RPM, in general, you also try to couple your experimental analysis with simulations. So with these simulations, you can get more detailed dynamic stiffness and damping coefficients. Knowing all of these dynamic coefficients, you then plug them inside your rotor dynamic analysis, where you actually test the stability of your rotor and the bearings, and you can gain if it is going to work or not. But that's all numerical. You have to put it into the practice, so I will skip this for the sake of being fast and being on time. So you have to experimentally verify all of what you did in the simulation side. So any shaft that is rotating will generate a sinusoidal signal if you put two displacement sensors. So here you have a displacement sensor to measure the vibration in Y. Here you have the vibration measurement in X. And when you plot them, you get something that's called shaft orbit. So you need to know the orbit because this defines if you are going to touch your bearings or not. So that's our system, that a typical assembly where we test all of this. And here I will just give you an overview that we have tested multiple different bearings, and here you see a set of bearing which shows subsynchronous vibration, which is deteriorating to your stability. And there on another hand, you have a set of bearing top foil and under foil, which gives you a very stable, a very clean peak at your rotational frequency, which means that it is void of any other disturbing frequencies that you don't want in your system. And here you see, let's say, what we call as the time chart, where you actually see the variation of the speed and the frequency with respect to the speed. And if you have only one peak like this is your 1x, this is where you are rotating, and this is supposed to be the dominant frequency. But if you start seeing something like this is really an unstable bearing design, and you want to avoid it. So, but this is purely based upon the structural properties and the damping properties of your bearing. And here on the right, you see another design where we can completely get rid of all of this, and we can have a stable system. So, concluding, of course, details matter, because we are talking about microns. the air film that we are working with could be in the range of 5 microns, 10 microns, 20, 30, 50 microns. So all of these are very important because the smaller you are, the more heat you produce and better thermal management of the system you need. Then of course you always need experimental test rigs, and you cannot only rely on softwares. And this is not the end. For example, you also need a lot of interest, or let's say a lot of attention when it comes to the thermal management of all of this system. Because you're producing heat, you need to dissipate this heat effectively in order to have a stable system. So yeah, thank you so much. Any questions? Yeah.
Yeah, first off, that indeed looked very complex.
Yes.
Sorry if my question is pretty simple. But according to your hysteresis curve, where do you start seeing the problems, at which speed or which frequency, when it, because it's damping and then you come back after releasing the load, and you have this shaft orbit, the eccentricity of the shaft. Have you experimentally tested when do you see problems there, or?
But what you refer to, for example, is a static test where we do not rotate the shaft. We just want to understand the structural properties. So you don't rotate the shaft, you just move it up and down against the shaft. So for example, this is the shaft, this is the bearing, you just move the bearing up and down just to give certain force to your structure of the bearing, and in order to record the response of it. So what you do is you load it, you get the force deflection curve, and you unload it, you get another force deflection curve. This gives you first feeling what will be the stiffness of your bearing and how much energy you can damp. So it helps you do, let's say if you have tens of different sets of bearings, you can understand which one is going to be the stiffest, which is going to be giving you the biggest amount of damping. And then you have to choose.
Right? Scaling damping.
Yeah. So the area under the hysteresis curve is your damping energy.
Okay.
So you get a first feel, like which one is going to give you good damping or good stiffness. So you have to choose. And then it's all experimental verification of it.
Okay. And while the system is running, you do the vibration analysis with 2 displacement sensors.
Yeah, exactly. Yeah, exactly. So this gives you the orbit of the shaft, and you try to see if this orbit is within your desired limit or it's exceeding your vibration levels of your limit that you set during the design.
And at which level does it exceed the limit?
That is something which you design. So this is something. So it could be a few microns. It could be a millimeter. So for foil bearings, it is in microns. You don't want to exceed it to certain microns. Yeah, please.
The minimum friction, does it correspond to the viscosity of the air? Did you
No.
test other gases?
No, we did not, because our system, yes, of course, it will depend on the viscosity of the medium that you're using, that's sure. But since our system is air breathing, so we tested basically with air, because we bleed the air from the compressor, so which is fresh air.
Maybe one question for me. Do you have any idea how these bearings will age as the materials, for example, deform over time?
We do have idea, but not experimentally verified. You see, idea we have based upon all the literature studies. So we select the materials that are resistant to corrosion, resistant to high temperatures. Of course, there is a selection of material. So this already tells you if you will have good enough life or not. I mean, there is tons of literature on the different materials on the foil bearings. And of course, we have experienced it ourselves in terms of the static structural stiffness and damping. But when it comes to how long would they last, experimentally, yet we have to verify them. Yes.
Yes, thank you, Danish. had two questions. The first one is concerning potential cooling. Can you say something there, if it's needed, if it's not needed, what you see there? And then now you did it with air, which is also the working fluid, but could you use another gas as then not the airfoil bearing, but then the working fluid bearing, which would somewhat solve issues you see if you would use other working fluids where you don't want them to get into the bearings, then you can actually start using those. So do you see any way to use them for other working fluids?
Okay, so remind me your first question, please.
So the the cooling.
Yes. So yeah, as I said, it's not the end part what I showed you here. You need to get rid of the heat that is being produced inside the bearing. So the power loss that we see in the different charts that I showed, that's the heat that you are generating within the bearing. You need to dissipate it. So for this, you need minimum amount of leaks that you have to carefully design, and then you have to see them in practice if it is enough. Because imagine your turbine is at very high temperature, so everything is super hot. You don't want this heat to affect your bearings such that your rotor bearing system is unstable, or the shaft is, you do not want your shaft to touch your bearing. So of course you need critical design or careful design of your leaks such that you can manage this thermal problem. On your second question, yes, we can design the bearings for any other fluid, given that we do let's say experimentation with it. I mean, I don't expect that the behavior of the static structural or dynamic structural properties will change hugely, but what will important is the power loss. That if by changing different fluids, if the power loss is being impacted too much, and then maybe we need a different kind of let's say thermal management in order to use it.
And what if the working fluid was a vapor?
Yeah, this as far as it is gas, it's fine.
Okay.
We don't want any liquid particles there, because as soon as you have some particle, either liquid or solid, you destroy your gaps and you destroy the system. No questions online?
Unfortunately not,
Okay.
but we had a good discussion here. So
Thank you.
thank you so much, Danish. Now we have the last presenter of the evening, Gerrit Vullner, and the topic of the presentation is heat pumps and chillers with natural refrigerants.
Thanks. And yeah, the last presentation, and I hope you're still awake. Yes, I will actually try to a little bit close the circle that Michel actually opened in his first presentation on what we're actually trying to do within Fit for Micro. We now deep dived quite significantly into pyrolysis oil, into bearings, but I will come back rather to the questions, and that's not reflected too much in my title of my presentation, but to the question, how does a system look like that we need for future heating in different applications, and where does the microgas turbine play a role? And then, and that's where this title comes from, which other components can a system include, and how should it be included so we can actually provide electricity, heating and cooling from a combined system. So, either one?
Yeah, either one.
I will just show this again with a question mark. How will the transformation of the heating sector look like? Currently, we are somewhere rather on the left side still. We have still quite some fossil electricity production, switching to renewable electricity production. We have a significant share of fossil heat supply, and also mobility is still mainly driven by fossil fuels. And where do we want to go, which are the scenarios we want to come to 100% renewables in a certain time frame, not too much time anymore, and we discussed this previously. One way is electrification of all and coupling of all sectors, electricity from renewable energy sources, electrification of heat supply, electrification of mobility, and bring it all together nicely in an interactive way, away from standalone applications. And I put a question mark there because reality shows that this is not so easy, and the real world is quite diverse. And all these single parts already to achieve these is hard, and to couple these is even harder. So another slide that I quickly want to show as an introduction. This is from a recent study where our institute was also involved. And they brought together recent studies on, let's say, scenarios for future energy carriers in the building sector. And what you see is that the current situation, we are still, well, it's in German, so I quickly translate. The green is biomass. The red part is district heating. It's heating networks. Then we have a large part, which is the light purple part, which is fossil fuels. And then we have a certain share already now of electricity, of course. And what you see, yes, all scenarios agree that the part of electricity will be much higher in the future, needs to be much higher, which actually means heat pumps, mainly for buildings, because, well, a decent use of electricity, and we come to this later, for heating is, of course, a compression heat pump. On the other hand, there is a certain bar here on hydrogen and e-fuels, renewable fuels. So, and they're starting from 2030, but later even more, there's quite some uncertainty between these, all these scenarios and studies. Some of them say that hydrogen and renewable fuels, as discussed here, will be negligible in the building sector, and others show relevant shares. And then the next question is, how does this impact decisions which are taken now, today, on infrastructure and on changes in infrastructure? And, well, the outcome of this overleaping study is that actually in many cases, these decisions now can only be taken really in combination with local bottom-up considerations, depending on really the local situations. And, well, this then comes back also to where does a fit for microsystems fit for heating of buildings in the building sector. Now, small excursion, what is a heat pump? Because a heat pump, everybody talks about it, but what are we actually talking about it? And I will also just stay on the main part. We use exergy, and that's not energy, it's exergy. To explain, it's the share of energy that has a certain value. And electrical energy is pure exergy, while thermal energy has a share of exergy only. And we use this to run a process which then pumps up low temperature heat to useful heat. And that's called a heat pump. Actually, a chiller is also a heat pump, because then you actually just reject this medium temperature level and you make use of cooling down a low temperature part, which is called producing cooling, which is a chiller. Now, there are many ways to build heat pumps. There are, and I will focus on the closed system and the compression heat pumps, and also explain a bit what a sorption system, a closed system is, because this is a way of thermally driving a process that produces cooling or heating. The others I will neglect for the moment. They also do not play a large role, at least not for building heating. Especially here, mechanical vapor recompression in industry is a big topic. So a compression heat pump is basically the same picture, but more in detail. We use electrical energy. It runs a mechanical compressor, which compresses a vapor, a refrigerant, and by this produces heat. Since I noticed that I only have 15 minutes, not 25, which I thought, I will not go in the details of the thermodynamics, but probably this is quite known. I will rather ponder a bit on another topic. The efficiency of a heat pump depends on the temperature levels, and this is really a big difference to the standard way we are heating currently, because condensing boilers, well, they do depend a bit on the temperature level at which they deliver heat. If they have to deliver at 70 or at 50, there's a small condensation effect. This is why they're called condensing boilers, but that's a few percent. For a heat pump, this makes a huge difference, and for a heat pump, there's a second temperature which is just not there for the condensing boiler, which is the source temperature, and this is mainly ambient. So for the example of outdoor air temperature, if you look at buildings, it gets colder, the temperature you need to heat the building needs to be higher because you have a certain heat distribution, you have radiators, or even the floor heating needs to be at higher temperature if you have a higher heat load, which is influenced by the outdoor temperature. And at the same time, heat pump efficiency, due to two effects, goes down due to the source temperature, and it goes down due to the higher heat supply temperature. This is an important consideration when you look at when heat is actually provided. Main heat, just looking at average temperature profiles, is provided somewhere in this region. There's a certain share which is provided at very low temperatures, but it's not very high temperatures either. So from this you get then the overall efficiencies that you can achieve with heat pumps, and that depends also mainly on the heat distribution within the building. So older buildings, not well insulated, need higher temperatures, so efficiency of heat pumps is lower. We have just a little excursion to the Fit for Micro project. We have tested a heat pump, which is a nice heat pump. It's run with the refrigerant propane. It's R290, which is a natural refrigerant with very, very low global warming potential. There's a big discussion currently on which refrigerants should be used in future, can be used. The issue with propane is it's flammable. So there's safety issues to be handled, but from thermodynamic properties, it's a very nice refrigerant. And also from climate perspective, it's a very nice refrigerant. And you can achieve quite high temperatures. We looked at here at lower temperature conditions, which A7W40 means air 7, water 40. And you see some efficiencies here, the thermal COP for these, which again reflects mainly the point that if you have to provide 30 degrees, efficiency will be higher than if you have to provide 40 degrees. So then we come to another technology that we want to look at. This is the thermally driven heat pumps, and we actually especially look at the case to use this for cooling. There you use high temperature heat to run the process instead of electricity. And why do we look at this? Because the microgas turbine does not only produce electricity, it provides heat. And we can either use this heat for heating directly, or in summer, for example, if you want to produce electricity and have a cooling need, you can run a chiller with it. I skipped this and rather show how much time's left. Yeah, I also skipped this. I can ponder a bit on thermally driven heat pumps actually as a heat source, but that's kind of an excursion to another topic. Within Fit for Micro, we want to look at the chiller application. And
let's start by watching some short video. This demonstrator consists of two glass bulbs. One of them is filled with sorbent. The second one is filled with pure water. The bulbs are connected with each other, and in the middle here you can see a valve. The pressure inside the bulbs is very low. It's about 20 millibars, so we can call it a vacuum. And in this position, the valve is closed. And now we will see what happens when we open the valve. We are opening the valve now. And here, what you can see here is the formation of ice. Okay, so once again, what has happened here? When we opened the valve, the sorbent started to suck in the water and the pressure in the right valve started to drop. Decreasing pressure caused the evaporation of water and decreasing its temperature, and that's why the water froze. So as you can see, sorption processes can induce evaporative cooling, just as a compressor does in all of the commonly used compression chillers and heat pumps.
Okay, so I hope you could see the example. I hope that it would even be nicer to be seen. The thing is that the adsorbent can actually evaporate water, and as a compressor does, and you see it in the ice formation. Of course, we don't form ice, but we have heat exchangers in there. Sorry, that's the wrong direction. No.
Let's start by...
Yeah, we have heat exchangers in such adsorption modules, and you heat and cool periodically these adsorption modules, and you produce cooling in the evaporator. And with this technology, you can actually build a system, combined heating, cooling, and power combination. And what we did within Fit for Micro then is to look at different use cases, at different building profile needs, load curves, and then in addition to that on, of course, all the infrastructure, what is available around, how does the gas or electricity grid look like, or is district heating available or not? These questions need to be asked before you can actually find the case for such a combined plant. And to do this, Michelle already mentioned it, we did a preliminary use case evaluation based on an Excel tool for mainly the two cases, combination of the microgas turbine with a heat pump, with a compression heat pump. So we have a system of a microgas turbine. Well, the backup boiler can even be the microgas turbine itself, and a compression heat pump. And we can use electricity from the microgas turbine to run the heat pump. We also consider PV in the system as a potential additional electricity source. And very important actually in such systems, storages, thermal storages, because with these you can actually do load management. And this is the basis that we will use and continue to use to design a system, first to be tested, but then also to evaluate in which circumstances and under which boundary conditions this technology can actually fit into which heating needs in a future energy system. So what we already, with rough considerations, did find is that, for example, if you want to achieve many full load hours, which is a requirement for especially the microgas turbine to run efficiently and cost efficiently, you should go to places where you have a year-round need of heat, which is, for example, in the health sector, in old folks lodging, because there you also, next to space heating, you have quite a high demand of domestic hot water. And with these, you can actually reach capacities, total demand hours, which are very high, and full load hours, which are also above 4,000 full load hours within a year. So for the cooling case, I already explained. There, probably it's not buildings, but it's rather in small industries where you have heating and cooling needs, and where you actually have to cover very specific temperature needs as well. So there, the evaluation looks differently, and it's harder to find good profiles and good demand profiles. But on the other hand, coupling CHP units with sorption chillers is really already being done, and with a cost-efficient microgas turbine, this should definitely work. So, as a summary, heat pumps make use of exergy to upgrade low-temperature heat, and the system efficiency is very sensitive to the different temperature levels, which makes it more difficult to size and design these systems correctly. And thus such heating systems need to be very well designed to fit the respective needs. And this also makes it more complex, which is a hurdle for implementing such systems, because a gas boiler still works much easier. So let's say the cost for the gas or for the fuel needs to be higher for such systems to be cost efficient. So, but there are potential use cases, and we will evaluate them more within the Fit for Micro project. Thank you very much. And I'm open to questions.
Even I have a question. So my question is about, in the project, your focus is going to be on using different types of, what was the term, refrigerants, or is it going to be on integrating the technology with other renewable technologies?
No, within the system, we will integrate specifically looking at integration of a propane heat pump and an adsorption chiller with the refrigerant water. So we will not do, let's say, detailed technology development for new refrigerants, but it's really on designing the system, sizing the system, and then having a good system control. There are very different control strategies, and they depend on how much worth is your electricity, how much worth is your heating. And that again depends on really the external conditions where you use this. So this is the considerations that we look more in detail, and more specifically what we will do is set up a system in which we can test parts of these scenarios, and in which we can verify also our modeling, because with you need decent modeling, system modeling, to then go into, well, let's say, more realistic scenarios and analysis of these, because that's another thing that was shown in these scenarios. Also, this big uncertainty comes from the fact that, let's say, how do you say, the quality of really modeling different technologies that goes in there is sometimes quite low. This is something that Alessandro showed. You can have a very basic description, or you can have a very high-level description. If you have a very high-level description, very detailed, it takes a lot of time, and you have to find the right level of detail. But for technologies like the microgas turbine, you have to take, as you have seen, take along quite some technical specificities to really show the advantage of a microgas turbine versus an engine. I mean, they are different, but from a larger perspective, it's a CHP. But you have to look more closely if it makes sense to take the microgas turbine or the engine. So that's the type of considerations that we look in.
You talked about the refrigerant. How much is inside a circle?
In which? So in the heat pump?
In a heat pump, yes.
That depends, but you can, that size of heat pump that delivers maybe up to 10 kilowatts of heating power. We have actually done work that you can do this with about 150 grams of...
150 grams?
Yes.
So your concern is about flammability, and your concern was about flammability of the refrigerant.
No, well that's, I mean, this is, let's say, current research going down with filling levels. Current heat pumps still have maybe a kilo, and then it gets different. But
I have
you can
20
reduce...
kilogram in my camping car and I'm still alive.
Well, let's say the principal consideration that people have their barbecue there, they have a big bottle of propane next to them, and then they say, well, but I don't want this heat pump because it has some propane in it. That's another debate, but I mean, that's reality, that this is, you just have to fulfill, and this is part of our work actually, not within Fit for Micro, but at Fraunhofer ISE, to show that you can really build safe heat pumps with propane, and we do all kinds of testing and development on that.
You'll be very lucky that you're still alive.
Well. Then, thanks.
Thank you so much.
Thank you.
I seem to have missed a couple of questions on chat because there are two features, one for question and answers and one for the chat. And so one is for Danish. Will there be metal contact during start and stop, was the question.
Yeah, there is always...
Yeah, maybe get the mic to you.
Yeah, so yes, there will always be a metal contact in the beginning. So this is what you want to reduce, let's say, the friction at the start. And this is why there are different solid lubricants that you have to use on your foils, which are stable enough at high temperature for a specific application, let's say for a gas turbine, which will reduce this friction. So of course, there is a friction, and that really also defines the life of the bearing, number of start-stops.
And another question was for Alessandro. Which software were you using for combustion simulations? Was
Open Foam and Fluent, right? Okay, thank you.
Yes. And then there is another question, which is mostly like a research paper, which is being asked to provide a summarized ranking of mature technologies under the analysis pipeline. I think that's all our dreams, no, come true. Yeah, I think this will take more than an event to answer. So if anyone feels interested, maybe they can just engage with the online participants. But otherwise, I would say we'll come to an end of this event today. Thank you, all of you, for participating. I'll thank the presenters for their really insightful and detailed presentations on various technologies, on various energy sources. And I think also want to thank all the participants, especially online from various countries at various timelines here. Thank you for your participation and also for the engagement. Yeah, so after hearing all the presentations, I'm really convinced that Fit for Micro project is very challenging, but also the really collaborative nature of the participants and their competencies and their ambition is going to make sure that this project is successful. Wish you all the best. And I also urge all the participants online and here to continue following the project. You can participate in the newsletter and keep following us to see where the journey takes us. Thank you. With this, we end the event.